discussed in the next 3 days. And the title of the conference itself says that science and technology of polymers and advanced materials through innovation, entrepreneurship, and industry. So in these 3 days, we will have 5 endowment lectures or award lectures. We will have 7 plenary lectures. We have about 50 invited talks and about 230 posters on display. So while we bank heavily on our academic strength, I think we should not lose sight of changing R&D landscape in the country and elsewhere. Academic jobs have become extinct while changing times have opened new opportunities. So as a practitioner of polymers, we cannot afford to lose or turn our back towards these new opportunities. Therefore, in this conference, we have introduced 3 new features. You might have heard that in India, roughly every month there is one unicorn born. Okay? That means innovation and entrepreneurship has become very important, and we cannot afford to just turn our back to that side. To educate our younger generation polymer students, we have a panel discussion on entrepreneurship and innovation, and this will give an idea where India is going and what are the new opportunities apart from typical academic jobs. So this is one new feature we have introduced. We'll have a panel discussion on 3rd day, that's 4th November. You might be knowing that the academic jobs are getting very extinct and very difficult, very competitive, and there are not enough opportunities for all of us to get those positions. Okay? But if you look at the other side, industrial R&Ds have come up in a large number in India, and there are a lot of opportunities in industry R&Ds. So to prepare our younger generation towards building their careers in industrial R&D setup, we have another panel discussion on industry, where industry leaders will talk about what is their expectation and how our younger generation can prepare themselves for this new area of industrial R&D while they are pursuing their PhD. The third one is maybe 30 years back when macro started, there were not many postdocs in the country, but today if you look, there are a large number of postdocs. And there is no platform to these postdocs in macro. Therefore, we have tried creating a platform for them. We have a session, it's a small session called Early Career Researchers, where postdocs can come and present what they are doing. This is an opportunity for postdocs to show what they are, and this is also an opportunity for us, academic people, and for industry to choose best of the minds from this conference. So these are 3 new features. The last one, we have 2 popular lectures on day 4. These popular lectures are meant to understand the R&D landscape in the country and also look at the economics of R&D in the country. So with this, as many of you would understand, organizing such an event is not an easy task. There might be some shortcomings despite of our best efforts. So we request you to forgive us if there are any shortcomings. Okay? But on behalf of the local organizing committee, I assure you we will try our best to meet your expectations and to make your stay in Pune a memorable one and scientifically very productive. Thank you very much.
Thank you, Samir, for giving an overview of the conference. May I now request President SPSI, Professor Ramakrishnan, to address the gathering.
Thank you, Sarika, and wish you all a very good morning. On behalf of the Society for Polymer Science in India, I'd like to welcome all of you to this exciting meeting which all of us have been waiting for a very long time. As someone mentioned, we have had a very long dry spell with the virus playing its game. And so it's a real great opportunity. I see a lot of enthusiasm among participants to be here and share their ideas and work with fellow researchers in the country. The Society of Polymer Science itself was formed in the early 90s and has had real stalwarts of our country's polymer area being presidents of this society. It started off with Professor R.A. Mashelkar, who was a director here at NCL, and then later on went to be the Director General of CSIR, who was there with us yesterday. And then we had Professor I.K. Verma from IIT Delhi, another doyen in polymer area, followed by Professor Ashok Mishra and Professor Shivaram, who's here. And some years ago, I took over as a president, and it's been a real honor for me to work with the members of the society for the last little over 5-6 years now because of the COVID. The attempts of the society is truly to bring scientists from all colors of polymers into one fold. Polymer science is an intrinsically interdisciplinary field. It brings engineers, chemists, physicists, theorists, and a whole range of variety to work on problems concerning long-chain molecules, which are fairly complex and poses challenges of different kinds to each of these communities. And as Samir said, I was really appreciative of the effort that this meeting has had to bring special focus on our colleagues who work in industrial R&D. And this is particularly important in the area of polymers. And the context in which polymers are being viewed today, there is a renewed need for us to dedicate ourselves to solve problems that seems to be of high concern as a country and as a world. Plastics is no longer viewed in the best of the terms in what it's able to deliver, especially in a public mind. So it is for us, scientists and practitioners of polymer science, to educate and also inform and also help remediate the issues that are presented to us in the context of polymer environmental pollution in the context of polymers. So worldwide, there's a drive to do this, and in India as well, I'm very pleased to see more and more people working in areas that help develop strategies to recycle polymers easily, and also develop strategies to ensure its final resting place in a safe and environmentally sound fashion. So before I close, it's very important for me to mention one important thing, and that is the Society for Polymer Science had slated its biannual meeting of the society to have been held in IIT Guwahati in 2020 December. Unfortunately, because of the pandemic, we have had to postpone it. And we were, as executive members of the society, we were dilly-dallying about when exactly to have it, because we were convinced that an online meeting is not what we want. We wanted something that is an in-person meeting that would bring us all together, just as we have assembled today here. And in the process of dilly-dallying, we suddenly were awakened by our young enthusiastic colleagues from NCL Pune, who mentioned to us that they want to hold a meeting, especially to honor our immediate past president and revered colleague, Professor Shivaram. Shivaram has been a passionate individual who has been pushing polymers and working for the cause of polymers in this country, polymers, polymer scientists, practitioners of polymers, students of polymers, and all of them. And it was so befitting when they mentioned to us that they would like to conduct a meeting to recognize the efforts that Dr. Shivaram has made, not only as an academic, but as a leader in polymer science. And was very apt, and so we had a discussion of the committee and decided that we will call this meeting a macro meeting. So this meeting was sort of this ideas of this meeting was sowed in NCL and taken forward by the enthusiastic support of ISER Pune and the ISER Pune and Pune University. So I'd like to have a special thanks to both Asha and Samir, who are the chairs and the co-chairs of this meeting, for having put up a fantastic program in such short notice. So I'd like all of us to give them a big applause for having done this terrific job in such a short notice. With that, I'd like to once again welcome all of you to this meeting, and I hope all of you would have a wonderful time. I'm looking forward to the jazz program. I didn't know Shivaram was a jazz enthusiast, but so am I. So on 4th, we'll have a great treat from an excellent jazz group, I'm told. I look forward to that. So thank you all and have a wonderful day.
Thank you, Professor Ramakrishnan, for taking us through the journey of SPSI Macro. May I now request Director NCL, Dr. Ashish Lele, to address the gathering and introduce our chief guest.
Professor Sir Richard Roberts, Dr. Shivaram, Dr. Ramakrishnan, Dr. Ashok Mishra, many distinguished colleagues who have come from outside India, leaders from industry, delegates to the conference, and my dear colleagues and student friends. Namaskar and a very, very good morning to all of you. It is indeed with great pleasure that I, Professor Jayant Udgavkar and Professor Kumbar, welcome all of you to the city of Pune, and particularly to NCL, ISER, and the Pune University. It feels just so very nice to be able to meet finally, after 2.5 years, everybody in person. So as Professor Ramakrishnan said, we didn't want to have this meeting online. We only wanted to have it in person. So it's such a wonderful occasion to see all of you here. Spectacular to see the auditorium so full with enthusiastic participants. It's also a special honor and privilege for me to welcome Professor Sir Richard Roberts today. I'm very grateful to you, sir, for taking time out of your very busy schedule and to visit the National Chemical Laboratory, and also to inaugurate this 3-day conference on macromolecules. For your benefit, sir, I'd like to introduce my lab, National Chemical Laboratory, to you and to some of those conference delegates who might have come here for the first time. The National Chemical Laboratory, a flagship laboratory of the Council of Scientific and Industrial Research, was established in 1950 with the focus of exploring chemical and related sciences at the most fundamental level, while at the same time translating new and known science innovatively to applications in industry and society. The motto of this laboratory is not only displayed in the main foyer of our laboratory, as many of you may have seen when you entered the lab, but it has also been imbibed and internalized by generations of scientists and students who have worked in this laboratory. Over the past 72 years of our existence, NCL has contributed substantially to the growth of chemicals and allied industry in India. Additionally, the lab has also contributed to dissemination of knowledge through MTech programs, PhD programs, special industry training programs, and more recently also skill development programs. In the coming decade, we are committed to working on 7 key themes which have been identified based on their relevance to India, our areas of strength, the stakeholder connect that we have, and the potential to make impact. NCL was one of the first research institutions in India to have created a science and technology incubator called the Venture Center, which is today India's #1 bioincubator and has at any point of time 100+ exciting resident startups. A few of NCL's innovations have also been translated into successful startups through our lab to market program, and we hope to expand this portfolio much better in the future. NCL established a polymer chemistry group right from the beginning, and today the Polymer Science and Engineering Division integrates competencies from monomer and polymer synthesis to polymer processing and all the way to depolymerization. With more than 500 publications in peer-reviewed journals, 150 patents filed in India and abroad, 40 US patents granted, 6 patents licensed, and several technologies successfully transferred to industry, the Polymer Science Engineering Division enjoys substantial academic respect and industrial trust. We at CSIR-NCL felt that with the pandemic more or less behind us, it would be appropriate for the laboratory to host the SPSI Macro Conference in person. We are thankful to ISER Pune and to the Pune University for co-hosting this conference. This is also a special reason for the timing of the conference, as the previous speakers have already said, because on November 4th, we are going to felicitate one of the giants in polymer science engineering and also one of the finest directors that this laboratory has had the pleasure of having, Dr. Shivaram, Padma Shri Dr. Shivaram, on the occasion of his completing 75 years. So this conference is therefore, we feel, a befitting event to recognize his scientific and technological contributions. We are so happy that the entire polymer community in India and many leaders in polymer science from outside India have joined us to celebrate this occasion. As I said earlier, we are especially happy that this event has been graced by none other than Professor Sir Richard Roberts, the 1993 Nobel laureate in physiology. So let me take this opportunity to briefly introduce him to you. Dr. Roberts has had keen interest in chemistry right from his school days. He earned his PhD from the University of Sheffield in 1968 in organic chemistry by studying the phytochemistry of neoflavonoids and isoflavonoids. After a stint in the Professor Giles Stombinger's laboratory at Harvard as a postdoctoral researcher, he joined the Cold Spring Harbor Laboratory, a private, not-for-profit laboratory that is in the top 1% of life sciences institutions in the world and is home to no less than 8 Nobel laureates. Here is where Dr. Roberts made the fundamental scientific discoveries that have changed the state of knowledge about the central dogma in biology, namely, how are proteins made from the DNA template. At the time Dr. Roberts commenced his work, the dogma stated eloquently by another giant in the field and the 1965 Nobel Prize winner, the French biochemist Jacques Monod, was that anything found to be true of E. coli must also be true of elephants. What was thought to be true in the microbe E. coli was that DNA makes messenger RNA, which acts as the template for protein synthesis. Though a lot was known about how the process of making RNA was controlled, the RNA itself was regarded as a mere messenger, with each RNA coding for exactly one protein. Dr. Richard's work, however, completely changed that view. He showed that gene expression works differently in E. coli and organisms such as elephants and humans, whose cells have a defined nucleus. His team elegantly demonstrated that each messenger RNA has regions that code for protein segments and others that do not. This led to the discovery that a combinatorial choice of which segments eventually are stitched together leads to multiple proteins formed as a result of such alternate gene splicing. Further, the non-coding parts themselves may regulate expressions by binding to the same or other messenger RNAs. Thus, from a mere messenger, Dr. Roberts transformed the mRNA into a major player in gene expression. This has led to fundamental discoveries on the molecular causes of several diseases. I would also like to highlight two other aspects of Dr. Roberts' career, especially this is something we are actively encouraging at NCL. One is the collaborative teams and thinking outside the current boundaries of your discipline. At the time of his Nobel Prize-worthy work, most chemist departments were probably in a denial mode about the existence of molecular biology. It took a team of chemists, biologists, and electron microscopists working together to make the discovery that he is attributed to. The second is his ability to seamlessly translate the deepest scientific insights into useful and profitable ventures. He is implementing this at the New England's Biolab, which he joined in 1992 as the company's chief scientific officer. Dr. Roberts has won many, many more accolades and recognitions. The list is too long to read, and I'm sure that you would rather listen to Dr. Roberts than to me. So I will conclude by once again welcoming Dr. Roberts and other delegates to this meeting, and I am looking forward to the exciting 3 days of this conference. Thank you very much.
Okay, well,
Thank you very much. Good morning to everybody. It's a pleasure to be here. I've been debating what I should talk about because I used to be a chemist, and I have some interest in polymers, but not the sort of polymers that you guys are interested in. I'm interested in biological polymers, proteins, RNA, and DNA. And I thought I'd just spend a few minutes telling you a little bit about how I got involved in this, and then some of the interesting things that have come along as a result of it. So I started off as a chemist, looking at some compounds that were in the center of a tree. And I read a book by John Kendrew, who won the Nobel Prize in Chemistry, called The Thread of Life, which described the origins of molecular biology. And by the time I'd finished that book, I knew this was what I wanted to do, even though everybody in the chemistry department said there was no such subject. Fortunately, there was one guy who said, well, yes, he thought maybe there was. And so I went and applied, and I ended up at Harvard. By chance, I thought I was going to go to Wisconsin, but because the person I went to work for was there. But he said, oh, can you just wait a couple of months before you come over because I'm moving to Harvard. I went to Harvard, which was really an immense stroke of luck. I met so many interesting and fun people there. And the project I was given was to determine in an RNA molecule what was the exact sequence of the nucleotides, the 4 nucleotides, A, C, G, and U, that were in this RNA. And a man called Fred Sanger, who is one of the few people who's won 2 Nobel Prizes, had developed the early techniques for determining RNA sequences. And so I went to his lab, I wrote to him, said, can I come? He said, sure. Went to his lab and learned how to sequence RNA, and then took the technology back to Harvard, and I turned out to, again, by chance, be the first person in the Boston area who was doing this sequencing. Now, at the time, people were sequencing DNA by copying it into RNA. There was no method for sequencing DNA. And Jim Watson heard through a friend that I was able to do all of this, and I guess someone told him I was reasonably good at it, because he offered me a job. I spent 10 minutes in his office. He offered me a job at Cold Spring Harbor and said, come down. And what he wanted me to do was to determine the sequence of a very small DNA virus called SV40. It was one of the smallest oncoviruses, viruses that can cause cancer, that was known at the time. And so that sounded fun. But before I went down, I went to a lecture at Harvard by a man called Dan Nathans, and he described the possibility of actually taking a DNA molecule like SV40 and cutting it into pieces with some enzymes called restriction enzymes, and they recognize very specific sequences in the DNA, and they cut it whenever it comes about. And that sounded to me rather interesting, and by the time I got to Cold Spring Harbor, there were 2 or 3 more of these restriction enzymes that had been discovered, and one of the first things I did was to purify those enzymes and then to look and see if there were more. And the reason I did it was because I wanted to beat Fred Sanger. Fred Sanger was interested in sequencing DNA, and I thought, well, perhaps here was an opportunity to really do it in a different way, using these enzymes and the specific sequences they recognize, and just basically by mapping to work out what the sequence was. Well, that turned out not to work, but you know, as usual, failure is often a good thing. It's not something that you should get discouraged about. And in this case, the restriction enzymes themselves turned out to be so interesting because there were many of them, they all recognized different sequences, and other people were interested in using them for other purposes, including making recombinant DNAs. That is DNA in which you take 2 separate pieces of DNA and join them together to make a new DNA that had not been found before. And so the discovery of these restriction enzymes really was at the very basis of the biotechnology industry. Without these enzymes, we probably would not have a biotech industry today, or it would have taken a very different route to get there. Now, that also led to some interesting interpersonal relationships with Jim Watson, because he said, well, I hired you to sequence SV40. But I discovered there were already 2 other groups doing it, and I'm not very keen on competing and just doing the same thing that everybody else is doing. And so I said, well, you know, I'm just not going to do it that way. Maybe these restriction enzymes will help me do it, but I'm not going to do it by the way you hired me for. And he got very angry about this. He used to froth at the mouth when he got angry. And over the course of 20 years at Cold Spring Harbor, he was constantly angry at me, I have to say, because I'm one of these people, if someone says, oh, why don't you do this? I always think, well, that's not going to be very interesting because they thought of it. I'd much sooner do things that I'm interested in, that I thought of doing, things that perhaps other people hadn't thought of doing. And I think this is also very good advice for young faculty members, postdocs, students. Don't just do the things that everybody else is doing. Always see if there is some new stuff that you can get involved in. And also, I recommend reading widely about things outside of your subject, because that can be really helpful. You never know when you're going to read something, as I did this book, The Thread of Life, and discover, well, that's so much more interesting than anything I'm doing at the moment. That's what I'm going to do. I'm going to follow it. And so that's really played off very well in my life. It does lead to a number of confrontations, of course, like the ones I had with Jim Watson. But I figured out a way to deal with that, and it was okay. And it's, in general, paid off for me extremely well. Now, thinking about DNA sequencing, I was hoping to use restriction enzymes, but of course, what's happened is much better methods have come along, and now there are some fantastic methods for sequencing DNA. We can basically sequence the DNA of an entire bacterium, maybe 2, 3, 4, 5 million bases in a single experiment. And it's really amazing what one can do. You get the pieces, and then you have to join them all together, and you write computer programs that will put everything together. And so coming out of this, the whole field of bioinformatics, trying to put DNA sequences together, working out what the signals are in the DNA sequence, where you should start making proteins, where you should start making RNAs. And of course, it was during trying to figure out where RNAs were starting that we discovered splicing and split genes. And so, again, by just always looking at the frontier, asking questions that other people are not asking, can be incredibly powerful. It can be a terrific way to do science. And not only that, it's great fun. My wife thinks I go to work every morning. I just think I go to play every morning. It's wonderful. It really is very, very nice. Now, one of the things that comes out of all of this is thinking about polymers, that there are many polymers that are needed biologically that we don't have at the moment. And I've become very friendly with a man called Bob Langer, who you may have heard of. He's a materials scientist at MIT, and he has more patents than anybody at MIT has ever had. And he and I are very good friends, and we talk all about things that are needed. And so we've been working on ways of making polymers, chemical polymers, that can be used in biological systems. So I am director of a company called In Vivo Health. What they're trying to do is to solve spinal cord injuries. When you break the spinal cord, usually the spinal cord doesn't repair. And Bob Langer came up with making a polymer that you could put in the spinal cord that would help it to repair. And we're just finishing the safety trials on that, and so far they've been going very well. And hopefully we will have a commercial product from that in a short period of time. But there are many other areas where in biology, in medicine, we need access to polymers that are consistent and you can put in the body. Maybe you want to repair a bone, maybe you want to repair a muscle. Putting things in this way. In the case of vaccines, we had to find ways of enclosing the messenger RNA in a lipid coat so that you could put it into the body and it would just dissolve, the coat would dissolve, and the messenger RNA would be released. And Bob Langer had found a very clever way of doing this, and he now has been making materials that will last for maybe a day, maybe a week, maybe a month, maybe 3 months, and you can put the vaccine in series of compartments, give it all to the patient at the same time, and you have release after 1 day, or after a week, or a month, or 3 months. And this is a way of giving multiple doses of vaccines in a single dose, which, if you're in the developing world, this is incredibly important because a lot of people only get their first shot these days and they never get any more. So I think you should all be looking for ways in which the work that you do in polymer science can actually be used in many different ways. It doesn't have to be just medicine. There are many other uses for polymer chemistry and many good things that one can do. And I think I would definitely encourage you to read about things, maybe not what you're working on at the moment, but where you think that what you're doing or what you're interested in could lead you into some new directions and serve mankind very well. And so I wish you every success going forward. I wish you success in this conference, and I appreciate your listening to me. Thank you.
Thank you, Professor Roberts, for delivering the inaugural speech and letting us know how important it is to read things beyond your subject and also not to get bogged down by failure. You know, it's a very important message. Now, may I request you to now formally inaugurate the conference by just opening the conference booklet? Thank you. May I now request Professor Roberts to hand over the plaques to the award winners. I'm going to announce them. Yeah, you can be anywhere. Yeah. So you have to be here. No, you have to be on stage. Yes. Yeah. So, Professor S.R. Palit Memorial Award goes to Professor Yves Nano. Professor Nano. Dr. S. Shivram Endowment Lecture Award goes to Professor Richard Hogenboom. Professor Hogenboom. Pronounced your name properly. Professor M. Sanatappa Award is shared by Professor Niranjan Karak from Tejpur University and Dr. P. Trivedi from Garda Chemicals. May I now request Professor Karak to come on stage and accept the award. Professor Karak. Dr. Trivedi could not make it, therefore the award will be handed over to him later. Professor Kaushal Kishore Memorial Award is shared by Dr. Sameer Chikali, CSIR-NCL, and Professor Surya Sarathi Bose, IISc Bangalore. May I request Sameer to come forward and collect the plaque? May I now request Professor Bose to come on stage and accept the plaque. Professor Bose. It's a great pleasure to announce Dr. Amol Kulkarni, CSIR-NCL, has been awarded with the coveted Shanti Saurabh Bhatnagar Prize for Science and Technology 2020. As many of us know, this is the highest scientific award in the country. I request our chief guest, Professor Richard Roberts, to felicitate Dr. Amol Kulkarni. This brings us to the end of the inaugural session. I would really like to thank Professor Roberts to take time out from his very busy schedule and come here and inaugurate the conference. The tea and there's high tea served both in the first floor and on the ground floor. I would request the younger members of the conference to avail the one on the first floor. It's easier, and then there are few stalls in the ground floor too. Thank you. See you back in half an hour.
किती करायचं त्यांना स्लाइड्स दिसले पाहिजेत ना
Already given. Yes.
Only later sessions where people did not get awards there.
At this stage, just finish it. Welcome back to the first session of this conference. It's really a pleasure for me to be chairing this session with 3 speakers. I would take just a couple of minutes to introduce these award lectures and the awards itself, so please bear with me. The award lectures there are 2 award lectures that the Society of Polymer Science India has instituted. One in the name of Dr. Shivaram, which is the Shivaram Endowment Lecture that we will listen to now. And the other is the S.R. Palit Memorial Lecture. These lectures, the institution of these lectures in the society was because of the initiative and hard efforts of people in our community. The Shivaram Lecture, Endowment Lecture came through the initiative of erstwhile students and well-wishers of Dr. Shivaram. And this was instituted a few years ago when funds were actually collected for this purpose and handed over to the society. We've had 2 earlier lectures, Shivaram Endowment Lectures. The first one was by Sawamoto, who gave the first lecture, I think it was in Trivandrum. And the second lecture was by Nikos Hadjikristidis from KAUST. And today we have the third lecture by another incredible polymer chemist by name Yves Ganou, also from KAUST, who would be giving the, my apologies, I'm sorry, the Richard Hugenboom will be giving the Shivaram Endowment Lecture this time. The other lecture was instituted by the Calcutta chapter, or the Calcutta chapter a few years ago when they hosted the macro meeting. Subsequent to that, they provided the endowment funds to institute the second lecture in the name of another illustrious colleague of ours, Professor S.R. Palit, who was instrumental in establishing a vibrant school in the area of polymerization kinetics in the eastern part of our country. And Yves has told me that he will recollect some of the contributions of Professor Palit during his talk and correlate the early efforts of Professor Palit with something that he's doing now. The other 2 awards, we have 2 other awards instituted in the society quite a long time ago. The first one is the Shantapa Award, and this is again in memory of the second big school of polymer science, polymer efforts in the country that was established in the south. Professor Palit and Shantapa were contemporaries in some sense, and they established 2 independent schools of polymer science in the country. And Professor Shantapa again was a person who examined polymerization kinetics quite extensively, using a variety of initiators, including redox initiators that could be done at room temperature and water. And the awards are selected by a committee formed by the Society of Polymer Science. And the awards were given to two individuals, totally four individuals, to the M. Shantappa Award that was given to Niranjan Karak from Tejpur University, and Trivedi from Garda, erstwhile Garda Chemicals. Both of these are people who have contributed in very distinctly different ways to polymer science. Niranjan, from the point of view of fundamental development in polymer chemistry, and Dr. Trivedi is an applied polymer scientist, an exemplary one at that, because some of the developments that he championed in Garda Chemicals has led to remarkable development of products. And subsequently, the process that he developed was commercially a very successful one and taken over by Solvay, and the Kishore Memorial Awards are instituted in the name of one of my colleagues at the Indian Institute of Science. Professor Kaushal Kishore was a physical chemist by training, a thermodynamicist, who brought fundamental ideas in thermodynamics to bear upon very interesting problems in polymer science. And he had an untimely demise. And in memory of Professor Kaushal Kishore, we instituted two awards to recognize young talented polymer scientists in our country. So these are individuals who have made significant contributions before the age of 45. And so we have two awardees who have been awarded the Kishore Memorial Prize. One of them is Suryasarthi Bose from the Indian Institute of Science, and the second is Samir Chikali from NCL Pune. So that much for a brief introduction of the award lectures. And without too much delay, I would like to invite the first speaker, which is the S.R. Palit Memorial Lecture, would be delivered by Professor Yves Ganou, who is currently at the King Abdullah University of Science and Technology in Saudi Arabia. Yves is a constant visitor to our macros over the years, and it's a real pleasure for me to invite him to deliver this S.R. Palit Memorial Lecture. He would talk to us today on the recent developments in polyether and polycarbonate synthesis using boron-based catalysis. Yves is a remarkable individual and has contributed immensely to understanding polymerization process, especially coordination and anionic polymerization. So without too much delay, let me invite Yves to deliver this lecture. Yes. One point I just missed mentioning, I'd like to thank one of our sponsors of this conference, and the Royal Society of Chemistry London is sponsoring this session of our conference. And I'd like to thank the Royal Society immensely on behalf of the Society of Polymer Science for their contributions and for their sponsorship of this session. Thank you.
Is it? Thank you.
Thank you.
Can you upload?
Yes.
Thank you. Is it working?
Sir, please give your mobile.
Huh?
You need the mobile?
You want my mobile?
Yeah. There's a SMS.
Okay. Oh, thank you. Thank you very much. So good morning, everyone. Can you hear me? Yeah, okay. First of all, I want to thank the organizer for the invitation. Okay, Dr. Asha, Dr. Shikali, also the leadership of ICER, the leadership of NCL. Always a pleasure to come back to India. But I think that this year it's a special pleasure. I think I have more than one reason to be very pleased to come here. First of all is we will celebrate my very good friend, Dr. Shivram. Okay, I'm very happy to be here to celebrate his contribution to polymer science and also polymer science development, and polymer engineering, polymer industry here in India. There is also another reason that is very important is that you will realize in my presentation that some of the research has been really triggered because I came last time in 2018 here for the presentation, okay? And this is because of Professor Ramakrishnan. We have now a collaboration with Unilever. And also because of Dr. Shivram, we have a collaboration with an Indian company. You will see that. I don't mention the name of the company because nothing has been materialized yet, but still in progress. So I am extremely happy, and I hope that the next time I come, maybe I will have more to say about my collaboration with Indian colleagues and with Indian industry. When preparing this talk, I had the chance, of course, to read a bit about Professor Palit, this memorial lecture. And I was saying to myself, well, it was the golden age, okay, the 50s, 60s, and 70s. Professor Palit, he was associated with Bruno Zim. I think that the generation, they don't know who is. Should I shut down this one? I think that I can use this microphone, right? Is it okay?
This is okay.
Yeah, I was saying that maybe the younger generation does not realize who is Bruno Zim, for instance, or Herman Mark. I mean, these people, very famous. Professor Palit was associated with them, worked with them. Just to share with you an anecdote, I did my PhD in Strasbourg. So Strasbourg was once upon a time very famous for polymer science. And as a PhD student, I was using the very first ZIM equipment to build, for light scattering that was built in Europe, the very first equipment built in Europe by Stockmeyer, okay? These names people are very famous. Stockmeyer came all the way from US as visiting professor in Strasbourg, and in 55, he built this equipment, and me in the 80s, I was using that manually to do a ZIM plot. So now you press a button and then you have a molecular weight, the radius of gyrations, but so this is because of the contribution of people like that we have a very vibrant society here back in India, like Professor Palit. So I just want to close my remark about Professor Palit mentioning that back in 47, he came back to India and then established research on kinetics of polymerization. And one thing that he contributed very much, and I am going to use today in my talk, is the concept of chain transfer agent. And you will see how it is important in polymer chemistry to use this CTA, chain transfer agent. As I said, in the 60s, 70s, it was the golden age of polymer science, okay? Today, we are not at all in the same situation. Landscape has changed. Society does not think polymer science or chemistry with essentially good eyes, okay? We are responsible for emitting as a chemist for chemical processes more than 30% of CO2 and all, okay, gases emission, we are responsible for that. So, and the society expects us to a bit clean the mess. This is what is expected. I know that Dr. Shivram has now a very strong course on sustainability and chemistry. I mean, this is a very important topic. And somebody mentioned this morning the importance of industry training our young generation to work in industry. And you would have to tackle these 3 points, okay? How can we reduce the carbon footprint in all processes we are working on? The second thing is that when you reduce the carbon footprint, you need also to develop techniques, technology to capture CO2. Of course, we have a means, but I saw somewhere that between now and 2030, across the world, project will be, I would say, sponsored to capture 1.6 gigaton of CO2. So once you capture that, what you do out of that? You need to store it, do storage, or also do chemistry out of that, okay? So as a polymer chemist, I wanted to really address this point, okay? The upcycling of CO2. Upcycling means that, why upcycling? Because we have a resource now, but also one day, we need to address seriously the question of ditching fossil resources, okay? How long are we going to use fossil resources to do chemistry? So now scenario are built across the world, for instance, to see whether it would be possible to build chemistry based on CO2. CO2 as a C1 carbon resource. Is it possible? I mean, and of course, you have to change all processes. And now scenarios are built so that in 2040, 2050, 2060, countries across the world say that we will be C neutral, okay? So it's a long way. So I had all this question in mind, and in 2015, I was asking myself, you know, as a polymer chemist, what can you do, for instance? And in particular, the question of CO2. So we had different approach. I mean, at least 3 approaches. We use CO2, for instance, to make cyclic carbonate, okay? Because instead of using phosgene or derivative of phosgene, we demonstrated that, for instance, with certain sugars, you can make a carbonate very easily using CO2. We also use CO2 for polycondensation reaction to make polycondensate. But today, I am focusing on one point, which is CO2 for making polycarbonates. But when we opened this research, 2015, we realized that it has been addressed for 50 years already, okay? 50 years of research. 50 years of research using only coordination chemistry. You have a zoo of ligands, of metal that have been used to make polycarbonates, okay? When I say zoo, don't take it bad. It's a very, rich, I would say, systems based on different transition metals, and then equipped with ligands to do this very important aspect, which is coordination of epoxide. You add a nucleophile, and nucleophile attack the epoxide, and then insertion of CO2, and then this is exactly what is going on in all systems. And eventually, since you are using transition metal, you end up having polycarbonate that are colored. You need to get rid of the chromium, of the cobalt, and so on and so forth. And then you have also the issue of toxicity. Anyway, this was our analysis in 2015. And we say, are we really going to enter this very mature piece of science with big names? These are very famous names, Coates, Williams in Oxford now, Liu in China, Darensbourg just elected to Academy of Science in the US this year, and so on and so forth. When you look at the company, then I realized that, wow, there is a discrepancy. Let me go to this first. There is a discrepancy between the research done all in good journals, JACS, Angewandte, and at the same time, very limited volumes. Who is really selling polycarbonates? How much in terms of tonnage? Ridiculous, okay? So, and when you look at, for instance, Covestro in Germany, Netherlands, not much. 10,000 tons, maybe, so not much, using heterogeneous catalyst and so on. So, and let us go back now to chemistry, and I want to single out the contribution of people and how the progress has been made and where we were in 2015. The very first contribution came from my good friend Jeff Coates, okay? Cobalt system, Salin ligand taking from Jacobson, and he obtained the very first 2003, 2005 polycarbonates. So, and people like Liu in China, they had the idea to use exactly the same system, but to add an ammonium salt. And just because they added an ammonium salt, a bi-component system, then jump off the activity. But the same Liu, what he did, and other teams, okay? Now what they did was to attach the ammonium salt to the cobalt system. And again, a very important jump. And why I mentioned that? Because we did almost the same with our system, and you will see soon how we could progress in the activity. So I was then saying myself, okay, all attempts to make polycarbonate by copolymerization of CO2 with an epoxide is based on coordination chemistry. But at the same time, obviously, industry is a bit reluctant to use and make it, to another scale. What is wrong with that? Can we have a simpler approach? And the simpler approach is the following, is that can we use, system that is very easy that you can buy from Aldrich, for instance, without using coordination chemistry. So I was very happy to see last year the quote by Macmillan, who said, I am tired of using transition metal, spending my whole day in the glove box, and then he was awarded the Nobel Prize last year for organocatalysis. So I ask myself is that if we provide a very simple system, maybe industry would be interested. That was my approach in 2015. And then we came with this very simple idea. Why the simple anion cannot work for making linear carbonate, okay, polycarbonate. And why, when you take an anion, whatever cation, you end up having essentially cyclic carbonate. Because this reaction is predominant over others. I mean, of course, this step occurs. You add epoxide, you add carbonate. But once you have one single carbonate linkage, then you have the predominance of the cyclization reaction. And we ask ourselves, can we try to address this question? How we can do that? And then we came up with this idea is that if you decorate the alkoxy, decorate means that you create a species that is less reactive. I mean that you take a Lewis acid, put in the presence of an anion, and then you have an 8 complex. And at the same time, if this Lewis acid can activate for one of the two monomers, for instance, epoxide, maybe we would have the means to avoid the backbiting reaction and force the system to proceed with a linear addition. And this is exactly what is happening. When you take a good Lewis acid, not all Lewis acid will work. That means that if you took a too strong Lewis acid, then you can block this one. That means the 8 complex is not reactive enough. So we tried different Lewis acid, and one that worked well was boron base. And on the top of that, instead of using aluminum, we use also aluminum. Then we can claim that we have a metal-free system. So when you do that, you put the very first triethylborane, then you are making an 8 complex, and you prevent this reaction. No cyclic carbonate at all. But at the same time, if you put an excess of Lewis acid, then this reaction occurs. And more importantly, I mean, this reaction is easy. CO2 can add easily to any kind of anion. But when you have a carbonate, you are blocked normally, unless you activate the epoxide. And this is the concept, okay? And because this concept worked well, then, as I said, all these 3 reactions are favored over this one, and then you can make alternating polycarbonates, okay? And then we tried to avoid any metal. We took, onium salt, and then triethylborane, we call TEB in the lab, okay? So what is the advantage of this? You can go to Aldrich and Boy, and tomorrow try. You put epoxide, you need just to apply 5 bar of pressure of CO2, and you end up having a polycarbonate. It's very, very simple. You don't need to have 10 steps of synthesis of your ligands, okay? So it's very simple. But this system has limitation, and I will touch on later on, okay? But it works pretty well. I mean, these are the onium salt that we tried, okay? And TEB, and then you mix the epoxide. It works for almost all kind of epoxide. Even with an epoxide that is very challenging, that is called glycidol, for instance. I'm not going to talk about glycidol today, but there is no restriction. And for instance, these are the results we obtained, the copolymerization of propylene oxide and CO2. I hope you remember the ton values for coats and Lu and so on. We are not bad. We are in the range of 500, okay? 500 is, of course, below the system of Lu, but much higher than the initial system of coats, okay? And then look at by Malditov, it's almost perfect, alternating propylene oxide and CO2. You have here 2 populations because one population has 1 more propylene oxide, okay? And it's very simple. Tetrabutyl ammonium chloride is the salt that has been used. TEB you can buy and so on. And the beauty of this system is very much dependent on the pressure of CO2. That means that if you reduce to 2 bar, you don't need even a pressure reactor. You can do that in a glass reactor. You end up having only 5 to 10%, very small amount of carbonate. That means that you are making a polyether with 5% carbonate. That means that you are making a degradable polyether, right? Then if you augment, then you end up having 64%. If you go to higher, like 30 bar, then you can have almost an alternating polycarbonate. Remember, the very first step, the very first publication by Coates, he used 50 bar in his cobalt system. So these are the crude product. Okay, you open the reactor, this is what you have. Compare with the chromium or cobalt base. Cobalt base, it's between yellow or orange color. So you need really to get rid of the cobalt before using your system. Okay, here it's white. Okay, and of course we need to eliminate the triethylborane. We need to wash to eliminate the triethylborane. So this is where we were in 2016, 17, but what next? Okay, we have system, we can polymerize, and so on. We can make small chains, we can make big chains, we can vary the content of CO2 and so on. But then what we try to do is to see what is the scope of this system. Okay, is it apply only for epoxide and CO2 copolymerization, or can we expand to other things? Expanding to other monomers means that you can contemplate other kind of applications, okay? Other kind of application means that you can, think of something different, just precursor of polyurethanes, for instance, okay? But what we realize that, of course, this system has some limitation. Although it's very simple, you can, as I said, all ingredients are commercially available, but you found one thing. The limitation is that it is not that appropriate for low molecular weight, low molar mass application. Why? Because for one chain, you need one TEB, you need one initiator. The activity is not high enough to use with the chain transfer agent of Professor Pallet, right? So then we came to the idea that, well, let us use TEB and onium system for high molecular weight application. Let us see what kind of application we can have. And then we thought of developing another generation of catalyst for, I would say, with much higher activity than you can use for low molar mass. And I will tell at the end of my talk what is the structure of these, okay? Okay, so this is the scope. I mean, I tend to generalize and say that almost all kind of oxygenated monomers can be polymerized with this system. We tried all these epoxide, and even this one has never been polymerized, never. The corresponding polymer has been obtained, in particular in India, by the way, for ISRO, by polymerization of epichlorohydrin and modification of the chloride, okay? But for the first time with this system, we could polymerize this monomer, even this monomer. So you can polymerize all kind of epoxide, you can co-polymerize, but you can also polymerize a monomer that is known to polymerize cationically, not anionically. Anionically, you can obtain 10,000 molecular weight with great difficulty, but with this system, you can obtain 100,000, 200,000 oxetane. And we demonstrated that we can co-polymerize cyclic anhydride. So in a regular anionic polymerization, the best you can obtain is alternating. One cyclic anhydride, one epoxide, and so on. But with this system, I will demonstrate that we can vary the amount of anhydride. You can make polyether containing ester groups, and even 5%, okay? So just because of the presence of TEB, and I explained how. And of course, we could polymerize also cyclic ester and co-polymerize with epoxide, and this is a very interesting monomer. And this has been published recently. This is a monomer whose sealing temperature is minus something. I don't remember, minus 30 or minus 50. My colleague, he knows that better than me. But for the first time, we could co-polymerize this, at room temperature. I mean, because of the triethyl borane, and I will explain how. And we could obtain what we call polyacetal, one epoxide, one aldehyde, and then you have a polymer that can be easily degradable just by putting an acid, then you get back your aldehyde. Okay, this is I think that the very first attempt at polymerizing at room temperature, successful attempt at polymerizing aldehyde. So this is what I mentioned, and also another thing that we did was to co-polymerize isocyanate. So when you try to polymerize an isocyanate, you end up having typically a cyclization. You have a trimerization of isocyanate into isocyanurates. But in this case, because of the TEB, we could co-polymerize epoxide and isocyanate and make very rigid blocks, polyurethane blocks, that we could associate with, for instance, polyether low TG to make block copolymers. Okay. So this is the scope, and I felt important that you know who are behind this effort, okay? Of course, so we did the early work on polycarbonate, but I said Senthil Bhupati, I mean, a graduate from NCL, by the way, now he's in the US, he first polymerized the azido epoxide, okay? And then Dr. Patil, also another graduate. Don't think that all my graduates are coming from NCL, but most of them. Dr. Patil, he was successful to co-polymerize at room temperature epoxide and aldehyde. And also, this gentleman polymerized Ming-Cheng Jia, the isocyanate to make polyurethane blocks. Dr. Chidara, he co-polymerized anhydride and epoxide and demonstrated that we can vary the amount of anhydride in the chain. And Dr. Liu, he co-polymerized different cyclic ester with epoxide. So what are the applications I'm going to talk about? This chemistry allows, okay? First of all, there are many people doing thermoplastic elastomers, right? Of course. And, but we were motivated by one thing. Can we replace polyolefins? Can we replace the plastic behavior of polyolefin? Polyolefin you cannot degrade. The best thing you can do is do pyrolysis, 400 degrees, then you obtain an oil. So can we obtain something degradable, comparable? And you will see that we can do. Another major question, I don't know much about India about this question, but in the West, I mean in Europe in particular, they are going to ban surfactants that are not degradable, okay? So you will see how we can make surfactant degradable using CO2 chemistry. And this is because of one gentleman, Professor Ramakrishnan, who after listening to my last talk, he said, oh, you should talk to Unilever. And then we have a collaboration with Unilever. They are testing now our surfactant, okay? Hopefully it will fly one day with the facility in Liverpool. And I said, of course, here we have elastomers, but we have also plastic behavior. We wanted to match the polyolefin. And as I said, we have now different means to have a polyether. You know, polyether is not degradable. Polyethylene oxide is very difficult to degradation. But if you use this anhydride, if you use dialdehyde, if you use cyclic ester, you can introduce just 5% randomly distributed. You don't change the properties of, for instance, polyethylene oxide, still crystalline, but now this time you can cut into small pieces. This is the idea. So I am going fast. For instance, as I said, this chemistry is very good to make high molecular weight. Here, for instance, you have the example by Ming Cheng. He co-polymerized two epoxide, octene oxide and cyclohexene oxide with CO2. Here you have a very soft block, minus 40, polycarbonate block, but minus 40, low TG. And here you have a high TG block, cyclohexene oxide carbonate, okay? So we call that cyclohexene carbonate, and here octene carbonate. You can go up to 300,000 molecular weight, and you have a nice phase separation, but your typical thermoplastic elastomer, but the thing is, the Young modulus is pretty low. That means that in this case, you are in the range to between 2 and 5 as a value in terms of megapascal for the Young modulus. But it behaves very nicely as a rubber, okay? And you can see here the strain behavior. And it's very good, almost between an elastomer and an adhesive, okay? And we cannot go higher in terms of Young modulus just because the carbonate is not the appropriate block for the, I would say, high TG block. And we have other solutions I am going to demonstrate later. The same gentleman did so-called non-surfactant CO2 base, okay? And this is what we are sharing now with the Unilever, okay? So we can make a dye block, a carbonate by copolymerization of ethylene oxide and CO2. We can make a dye block, we can make tri-block. And so this is what they are trying to, as a surfactant, to replace existing non-ionic, very old PEO, PPO type surfactant. Okay? And these are totally degradable, and they are very sensitive, and they can be easily degradable. Okay? So, as I said, Ming Sheng polymerized this monomer. This is the isocyanate. Okay? Normally, if you do that by anionic way, you end up having a trimer. You cannot copolymerize, but he was able to copolymerize just because of TEB. TEB make an 8 complex. The 8 complex homopolymerize and copolymerize and does not give any trimer. So here you have the GPC, you have the Malditov. It's pretty well controlled, and we could make, for instance, tri-block copolymer. So when I say tri-block copolymer, here you have the 2 outer blocks that are polyurethanes obtained by copolymerization of propylene oxide, and this isocyanate. Here you have a low TG block. And look at the situation. Here you have a typical high-density polyethylene and low-density polyethylene. We compare nice, right, in terms of strain, in terms of stress at break, and so on. Okay, so, and these are totally degradable, I would say, polymers. And of course, at this point, we cannot compete economically. How can we compete economically with high-density polyethylene at this point? But at least we could demonstrate that we have something that can match mechanically polyolefins and that are totally degradable. So the day government in the world will put a carbon tax on the amount of CO2 released because you are making ethylene, because you are making polyethylene, maybe we can compete. But we are not there at this point because no one cares about releasing CO2 at this point when you make ethylene or polyethylene and so on and so forth. Okay? So, and then we also had a work on the copolymerization of cyclic ester and cyclic ether. So this is something that does not happen. That means that you can make block copolymers, but you cannot make random copolymers unless you are using this technique of TEB, okay? And these are the salts that have been used, essentially. These are the monomers and so on. So we polymerize easily, for instance, lactide, and then you can make blocks and so on. So here, for instance, I just wanted to emphasize this is high-density polyethylene, low-density polyethylene, and this is the kind of behavior that we have with our block copolymers made of polycarbonate, polyether, and polylactide. So you can have, depending upon the size of the central block, the size of the external block, you can have a plastic behavior or a pure rubber. Okay, here you have a pure rubber, here you have a plastic behavior. So again, we wanted to contribute to the area of, I would say, degradable plastic and rubber, okay? And with a monomer that is cheap, lactide is very cheap, okay? And we are still looking for large-scale application of lactide, and I think it's much better than, I would say, the pure polycarbonate, old polycarbonate thermoplastic elastomer when you take the case of mechanical properties into account. So just to show that this chemistry is very easy to be applied, I mean, this is done by my colleague, Dr. Alagi. He did not graduated from NCL. He went up to Korea to obtain his PhD. But what he did was to, using raft, make a polymethacrylic acid and use the carboxylic acid to grow chains of, typically polycarbonates. And what he did was to use a short backbone and a very long backbone. So depending upon the backbone, you can have a kind of sphere type graft copolymer. Sphere means that the backbone is very small. You have a typical sphere, and when the backbone is long, that means the polymethacrylic acid is long, you have this elongated morphology that he could unveil by AFM. Just to show you that provided you have carboxylic acid, you can easily generate polycarbonate using this chemistry. So this is something that I mentioned earlier, and this is a recent addition by Dr. Patil in my lab, is that we targeted this monomer that has been essentially homopolymerized at minus 80 degrees below the sealing temperature. And I don't think that there is an attempt even to copolymerize this monomer. But you can do that at room temperature using TEB. Why? Because you have here, in the presence of TEB, you have this kind of species, and this is an 8 complex. The 8 complex add one monomer unit, and immediately after that, because the epoxide is activated, you insert a monomer. Okay? So therefore, no way to have, I would say, a reverse process. You have a depolymerization. And therefore, you can make an alternating one dialdehyde, one epoxide, and so on. And this occurs because of this one. Because you activate the epoxide, and this is able to add. And then once it is introduced, it cannot depolymerize anymore. Okay. So this is the trick we played. And what he did was to go next. And then, of course, the polyacetal, you put an acid, you can degrade easily. Okay. What he did was to homopolymerize any kind of cyclic ether and to add sequentially some of these dialdehyde. And then you can have a polyether containing some acetal groups. 2 minutes. Oh, yeah, I'm speeding up. Sorry. And then you have a polyether that is degradable just because of the introduction of this phthalaldehyde. Okay, I am going fast just to say that this chemistry works also for epoxide, CO2, and anhydride. And that means that you can control the insertion of anhydride, because normally if you don't have this TEB, you can only have alternating. You cannot do, and this is the kind of thing that because of the presence of this Lewis acid, the structure that you can have. Of course, you can have an alternating copolymer. That means that one epoxide, one anhydride, and so on. But you can make an ether-rich polymer or ester-rich polymer. You can have different kind of distribution. Okay. So why ether-rich is interesting? Because you have inserted this anhydride, that means an ester group, that is cleavable. You can easily cleave. Okay. And it's very cheap chemistry, and anhydride is very cheap, epoxide as well, and you can make easily degradable system. So, yeah, I know that I have only 1 minute, but or even less, but I will eat a little bit of my time maybe. Just to mention that we thought that, okay, we have the chemistry that is very cheap, or to some extent, very easy at least, And these are the precursor that we can make, and we can make easily, for instance, foams, okay? After eliminating the triethylborane, ammonium cation, recycling, and so on and so forth. But the question we ask, the industry asks, is it economically viable to make foams? No, because you need too much of TEB, and TEB is not that cheap. Okay. So then that brings me to the next thing, and I have a few minutes, 1 minute or 2 minutes. You know, this is the system I have described so far, okay? But now if I go to the next, which is a bifunctional catalyst, remember the works of Liu as compared to Coates, right? He attached the ammonium salt to the center, cobalt center, to activate the monomer. This is exactly what we did here. We attached 2 boron to this ammonium and so on, okay? And look at the situation, okay? So I go fast. We try to homopolymerize. It works also for the copolymerization. Just give a look at the activity. These are all the systems that have been used, that you use currently to polymerize any kind of epoxide, okay? So industrially included. So this is the activity, okay? It's extremely, extremely fast. Now we have the means to move to the use of chain transfer agent, right? And this is exactly, so here we demonstrate we can go to very, very high molecular weight, millions of molecular weight, no problem. GPC, so on and so forth, is very good. Look, so here typically 20,000 monomer for 1 molecule of catalyst. So we are talking now about ppm level, or if not for ethylene oxide, ppb level works, okay? And here you have, you know, the amount, okay? 10 to the power 5, and only 1 catalyst, 25 chain transfer agent contribution of Professor Pallet. Here you can understand. Now it is workable. You can make small molecular weight. The chain transfer agent is very cheap, okay? You just put 1, and we are talking here part per million, part per billion here, and still the TOF is much higher than the one of Liu using cobalt, remember, okay? So, and then it works also for oxetane. I close my presentation saying that it works also for CO2 copolymerization with epoxide, with value in the range of less than 1,000. And look, of course, because of slow CO2 use, you slow down everything, of course, okay? And therefore, you need to use a little bit more as compared to the previous case of homopolymerization, but still 20,000 monomer for 1 catalyst, okay? And then just I wanted to conclude saying that I think that now we have a portfolio of a system based on boron, one for high molecular weight, obviously. You can make thermoplastic, you can make different types of polymer that can be degraded and so on. And you have also a system that we call bifunctional that you can use in the presence of chain transfer for low molar mass application. And this is what we are working now with industry to promote this system. I want really to thank my co-workers because they are very, they understand my approach, okay? This is not a lab where we focus on publishing at any cost. But what we really want to focus is to address the question of CO2 use, the question of sustainability, the question of transferring to industry. So these people, they spare no time making kilograms of sample that we distribute to industry. And I would like to thank them, okay? All of them, okay? And of course, my 2 colleagues, Nikos Hadrikousidis, he has a talk this afternoon, and tomorrow, day after tomorrow, my colleague Sanjay Rastogi. So just to advertise a bit, okay, we with Nikos and Chris Matiaszewski and Muthu Kumar, we edited a book, 5-volume that is called Wiley published Macromolecular Engineering. In that book, I wrote a chapter about polymers and sustainability. What are the scenarios to go to really a circular polymer economy, right? So, this is the book and this is the chapter. Thank you for your attention.
Thank you, Eve, for a really illuminating lecture. The seminar is open for questions, maybe a couple of questions. Yes, please go ahead. Yeah.
Hello. Yeah. Thank you very much for such an interesting talk and possibly some paradigm shift in some cases. Now, the monomers you're using is also like epoxide, which can homopolymerize, and you are also showing in some cases. Do you see some homopolymer synthesis during copolymer synthesis? And if you see homopolymerization, how do you avoid that?
I don't understand. I am almost deaf. Okay, so you have to speak loudly and make it very simple, your question. Yes.
Eve, the question is, do you see the formation of homopolymers when you're trying to polymerize epoxide with carbon dioxide?
No.
Not at all?
No. The CO2 is very easy to be incorporated. It reacts very, very easily with any kind of anion. Okay? So the issue is not to avoid homopolymerization. The issue is to decrease the amount of carbonate. How you can have, for instance, a polymer with only 5 to 10%. Okay? If you take a monomer like cyclohexene oxide, put with CO2, it's very easy. You are obtaining 100% alternating. Okay? So, of course, if I say 5% carbonate, how can I swear that all chains contain at least one? It's very difficult, okay? So maybe you have some homopolymer. But do not forget one thing. CO2 incorporate very, very easily. And alkoxide will eat first the CO2. You really need to put an activator, an excess of boron to activate the epoxide to favor the homopolymerization of epoxide. Otherwise, the CO2 will be eaten.
Thank you very much.
Any other questions? Yes.
Sir, it's very interesting talk. So I have a question that the CO2, the purity of a CO2 also would influence on your kinetics, correct?
CO2?
The CO2 which you are using, maybe you must be using very high pure CO2.
Yeah.
Correct. Suppose your real CO2 you want to fix it.
No.
So definitely your chain transfer control going to be a very tough challenge.
I think that this is a good point. We spend at least 6 months to develop a system to dry the CO2, because otherwise it's very difficult to control the molecular weight. This system is tolerant of water, okay? So if you have water, then you reduce. It does not kill the system, but participate. But then we had to buy a drying system from Korea and China, South Korea, to dry the CO2. Because if you use the so-called CO2, then you cannot really control molecular weight. It is controlled by the water present. Okay.
All right. I think we'll reserve this question for later because we're running out of time. Yeah. So Nikhil, you can talk to him later. Okay. Thank you very much, Eve, for the fantastic presentation.
Yeah.
The next speaker is Professor Niranjan Karak from I'll get you the microphone. From Tejpur University, and as I said, I will stop at 5:25. Yeah. And Professor Karak will be giving the Shantappa Award lecture.
Thank you, sir. Good morning, still 5 minutes is there to one and all. At first, I thanks the Society of Polymer Science, India, for awarding one of the awardees for this prestigious Professor M. Santappa Award. As a part of our humble effort for sustainable development in the field of polymers, today I am presenting before you this biodegradable smart polymer nanocomposites as sustainable material for multifaceted advanced applications. This sustainability, as already mentioned by the earlier speaker, is not a barge phase, rather it is the requirement of the day, and as it not only fulfill the demand of the present generation, but also it take care the future generation needs. Thus, it is not any special zonal or local development. Rather, it is more than combinations of economical, environmental, material, and human resource development. Here, I shall talk on material development. As you know that this materials importance is recognized from the ancient times. That's why we know that Stone Age, Bronze Age, and now is the polymer age and nanomaterials in coming into the picture. Thus, most of our materials are made up of that metal, ceramics, polymer, nanomaterials, or combination thereof. Now, if you see, today most of the other materials are being replaced by this youngest member polymer in the material family. Polymer is really a wonderful material which is gifted by the nature from the day when life has been created by the fantastic combination of carbon, nitrogen, hydrogen, oxygen, etc. And now it is further enriched by the effort of the scientists, polymer scientists. And it is known to you that this, due to their inherent characteristic, which are not available in any other kind of material. However, because of their so much advantage, we are using them day in, day out, from the bed to the bed, even in any scientific development or even in our bad time, they are the best friend. And as a result, with increasing population and comfort in our life, we are creating environmental havoc out of this polymer. Besides this, polymer also, most of the polymer depends on the fossil fuel resource, which is a fixed resource, and hence they have this resource problem. In addition, they have waste disposal problem, land filling problem, risks to the aquatic and terrestrial animal, overall adverse environmental impact. And non-renewability of the resource and non-biodegradability of the ultimate product are the main cause for such adverse effect to the environment. Now, then question definitely, what should be the right polymer? According to the sustainability, you need a polymer which are either not dependent or very low dependence on the fossil fuel or the fixed resources. Further, they must be environmental benign, biodegradable, and they should be part of the sustainable development. And most importantly, they should refresh the environment, because environment is already polluted. Just now you have seen how carbon dioxide can be used, but if you can reduce the carbon dioxide in your process, then carbon credit can be achieved, which will also help to refresh the environment. And your approach must follow the triple bottom line approach concept, which is associated with the society, economy, and ecology. And literature advocate that bio-based resource may be one of the best choice because it will fulfill all the demand what we are looking for. Further, it can also start from the environment or nature and end up to the nature. Thus, it may lead to sustainability. As a polymer scientist, we know that architecture also have significant contribution in performance and processing of polymer. Besides linear conventional polymer, there are other architectural. In our research, we have tried to concentrate on hyperbranch polymer because hyperbranch polymer having the advantage like other dendritic polymer, that means they have large number of terminal functional group, they have high solubility, low melt viscosity, and hence high applicability, and most importantly, they can be synthesized like conventional polymer by a single stage or single step process. Thus, in our endeavor, we have started with polyester, because polyester outranked about 54% in the coating and paint industry, and it is the simplest organic reaction, and it is compatible with many other systems. However, polyester has the problem of low alkali resistance. Thus, we have tried to incorporate some alkali resistance moiety like amide moiety, and tried to give a suitable marriage between the ester, flexible ester, and tough and alkali resistance amide, polyester amide. These are also biodegradable like polyesters. Our main focus is on bio-based hyperbond polyurethanes, where we have tried to get almost all kind of polyurethanes to get that smart attributes that I shall discuss. Besides this, we are also trying to develop the bio-based hyperbond epoxy to address two main issues: brittleness character or low toughness, and non-biodegradability of industrially used epoxy resins. All these polymers are mainly synthesized by using solution technique. Hence, solvent is an important issue because of the VOC, flammability, odor. So, our effort was given how to get this water-borne system, using water as not only as the media for the synthesis, but also for processing. So, in this endeavor, we have tried to get water-borne hyperbond polyester, where different types of bio-based resources are used, and without using any solvent, catalyst, and neutralizing agent, we are end up with a water-borne hyperbond polyesters. Now, some part of earlier all this synthesis, we have used some petrochemical feedstock. Here, we have tried recently that fully bio-based water-borne system can be developed, and this is one example where we are successfully developed the fully bio-based water-borne hyperbond polymer system. But whatever the architecture, or whether you are using organic solvent, water, always there is a problem. Virginity is not virtue in case of polymer, because they suffer from low mechanical strength, high flammability, and hence conventional composite system or field system has to be used. And they also suffer, we know, that processing difficulty, loss of transparency, lightweight, and hence the incorporation of nanomaterial or polymer nanocomposite is coming into the picture over the last 2 or 3 decades. Hence, we have tried to utilize almost all type of nanomaterial from 0-dimensional, 1-dimensional, 2-dimensional nanomaterial, nanoclay, cellulosic nanofiber, reduced carbon dot, reduced graphene oxide, all this into the polymer systems. And here it is necessary to mention that 2 of our adopted technique really addressed or noticed by the researcher. One is ultra fast reduction of graphene oxide to reduce graphene oxide by phytoextract and using metal catalyst. Within 5 minutes, you can reduce almost quantitatively without any using hazardous chemical. Another, this carbon dot, which we have synthesized by very simple just heating technique using even a glass bottle, using any carbohydrate which are soluble in water. And they can also be reduced by the same strategy, and they have interesting photoluminescence behavior which can be explored in polymer nanocomposites. Now, if you incorporate very little amount of this nanomaterial into the polymer system, you will be able to see that you are improving mechanical property, particularly tensile strength, toughness, others. But most important is the elongation at break. Here, generally, whenever you incorporate the nanomaterial, the elongation at break reduced. But in our case, we have seen that elongation at break even increasing significantly. And then we have tried to understand it, and we have explained it that due to the release of the hidden bond length and rupture of the sacrificial bond along with the slippage of the whole layer or sheets of graphene oxide, the cause of such elongation at break. Now, as in this presentation I told you that we will talk about smart material. Smart material mainly safe memory, self-healing and self-cleaning we have addressed. And if you see that this material as a safe memory material which can memorize the shape of their deformed fixed shape is smart switcher, smart expandable stain, scaffold material, artificial muscle, etc. Now, these nanocomposites, bio-based hyperbunch polyurethane nanocomposite using different types of nanomaterial, we have seen that you can use different kinds of stimuli from non-contact to contact, and you will get excellent shape fixity as well as very fast shape recovery. This one of the nanocomposites made up of castor oil based hyperbunch polyurethane with iron hydroxide and reduced graphene oxide based nanocomposite, where you can see that it is very fast recovering the shape within 22 seconds, and it can form self knot. Especially, you can lift about 235 times of its own weight by help or utilizing this shape memory effect. Some of these hyperbunch, bio-based hyperbunch polyurethane nanocomposite, say using sulfur decorated reduced graphene oxide, they are self-healing like plants and some of the animals. This healing efficiency, if you see, that is very high, and we are not adding or incorporating any external healing agent. Whereas you can get repeated healing without losing any healing efficiency by using microwave, even sunlight, which is easily available. So different types of nanomaterial you can incorporate. Titanium oxide, reduced graphene oxide nanohybrid. By changing the combination, you can get different types of smart attribute, self-healing, repeated self-healing, self-cleaning that I will show you. And this depends on the amount of nanomaterial you are using and also the stimuli what you are using, whether you are using high energy, low energy, what is the dose level. Based on that, efficiency will vary. The mechanism we thought, because without using any self-healing agent externally, how it is happening. This is purely micro-Brownio movement of the soft segment flexible chain. Here, this nanomaterial acts as a nanoheater, which absorbing the heat energy for microwave or sunlight or heat energy and distributed throughout the matrix, reaching to the glass transition temperature, and hence flexibility or flexible segment easily move from the one end to the other end and healing the damaged surface. Most significantly, if you see, if you can also get self-healing cleaning characteristic by lotus apex, super hydrophobicity with nano and micro nanostructural roughness on the surface. One of these material, we have shown that if you coat on the surface metal, glass, then it not only clean the surface by droplet of the rolling down the droplet of water, but also delaying the ice formation, which is very useful for different practical applications. This self-cleaning can also be obtained by photocatalytic effect, where by absorbing the light energy, here sunlight we have used, and they excite the electron which generate the superoxide or hydroxide radical, and that oxidize the organic contaminant like surfactant. Just now we listened that surfactant resulted pollution to the environment. And that surfactant, by using just sunlight, 96 to 97% you can degrade within 1 hour or so. This self-cleaning, as I told you, that the titanium oxide and reduced graphene oxide combinations, by changing the amount of this titanium oxide, If you use more, then you get self-cleaning attribute. If you use the reduced graphene oxide mode, then you will get self-healing attribute. So by changing the composition, also you can play around the smart property of these nanocomposites. This nanocomposite, which we have synthesized by a very benign technique without using any solvent, catalyst or neutralizing agent, and where carbon dot is used as one of the reactant. So without using any catalyst, we got not only the improvement of mechanical property, but also it is showing very interesting photoluminescence property, which help to get auto-cleaning surface. Further, it can show the wavelength dependent photoluminescence behavior. This same polymer, by using titanium oxide decorated carbon dot, you will expand the canvas of applications, where not only you will get surface cleaning, but also antimicrobial, and most significantly, you will get very selective membrane, which can separate selectively and water crude oil mixture, and you can see there is no crude oil which is separated out. And this can be repeated without losing any efficiency. This another field of application of this smart material is biomedical, where we have shown that switchering for which you, surgery for which you need switchering, and whatever the doctor expertise is there for particularly major surgery, it's either loosen or tighten, both of which is delay the healing process. And here we have shown that using this bio-based hyperpunch polyurethane nanocomposite of reduced carbon dot, which is also biocompatible, you can within a 15 seconds, you can make the knot by using the body temperature only, 37 degrees centigrade. And this is biodegradable, so there is no need of second surgery to remove the switcher. This blockage of the tube, both cardiovascular or even in the binary tube, you need expandable stent. But this expandable stent, what used either metal that injured your cell, healthy cell, and the metal polymer which causes biofilm formation, and hence again blockage and replacement. Here we have shown that this is not only this expandability, self-expandability at body temperature is almost near to 99%, but also it has antimicrobial activity. Hence biofilm formation will not be there, and you need not to replace within a couple of years. All these bio-based hyperpunch polyurethane nanocomposites, they are biocompatible. As we have shown cell viability as well as histopathological study, where major organ shows there is no alteration after post implementation of this product. Further, scaffold, it is used as a scaffold for this bone regeneration, where we have shown that oyster rat deliberately damage this tibial bone, both side and single side, and using our scaffold within 45 to 60 days, this will heal completely, whereas this will not heal even after 90 days. Thus, this can be used as a scaffold for bone healing purpose. However, this kind of bone healing scaffold requires surgery, which is painful to the host. So we have tried to develop a injectable bone tissue engineering material by using peptide modified carbon dot with the bio-based hyperpunch waterborne polyurethanes. And there, if you see, when we injected in the damaged area, within 2 to 3 weeks, there is a calcium deposition, osteoblast formation, and neoformation of the cell, which are required for bone regeneration. And hence, bone repairing or tissue engineering we can use by using this injectable material. All these materials are biodegradable, as I told you, and this we have tested by using soil burial test as well as microbial birth culture technique. And both tests confirm that the material, pristine material as well as nanocomposite have good biodegradability within the stipulated time. However, as you know that there is a need of life cycle assessment before going to the actual applications, because this life cycle assessment, which is cradle to grave analysis, that will give you the exact designing formula methodology to reduce the impact, environmental impact and health issue through the inventory analysis, impact assessment and improvement analysis. Where I have shown one example using this bio-based system, where you will get the advantage even though you will not able to 100% get rid of all these adverse impact even by using bio-based system. So in our humble pit at the corner of the northeast of India, we have tried to utilize this bio-based sustainable material in different field from active surface coating. Here we have developed some of the coating which are used by the industry, auto cleaning paint, industrial immobilization of the enzyme, which will not only stabilize the enzyme, but also it helps to enhance the activity, and you can use this enzyme repeatedly by recycle. This is iron oxide used as the nanomaterial here. This bio-based material, as I have shown, that it can be used in tissue engineering. They are one of the work what I have not shown is heterogeneous, very selective catalyst. This bio-based nanocomposite you can utilize to get 100% selectivity for ferrohydroxylation of substituted aromatic compound without just the substitution, whether it is electron withdrawing or electron donating. We have also patented some of the work where we have used as a biosealant nanocomposites. Then we have also used anti-cancerous and antimicrobial material, anti-static material, safe memory and self-healing I have already shown. E-pollutant removal we have used. Most importantly, our one of the work shows the anti-counterfeiting attribute. This anti-counterfeiting attribute is not only showing the different color or the impression what you have under UV light, but also it improves the mechanical property of the coated surface, and hence in currency in your security system this can be utilized. So this bio-based, bio-derived engineering material have high demand in various applications for value addition of multifaceted, multidimensional material. A result shows that both the starting material as well as end product have requisite grain material characteristic with targeted sustainability. Use of such approach not only makes the environment clean, but also it try to utilize the concept of triple bottom line approach. Thus, using such approach can clean or refresh the environment, and multifunctional nanocomposite have multifaceted advanced applications. Thus, in our research, we have tried to address the fixed stock which can be renewable and which can be obtained from bio-based natural resource. We have talked on VOC generation, which can be controlled by waterborne system, and also we have shown how you can refresh the environment in some extent through this approach. I must acknowledge the different funding agencies, both from the research organization, institute and industry, as well as my collaborator who are helping particularly for the bio work, and recognition wherefrom we have received or appreciation time to time we received from the different magazines or reports. However, this work has been done by my student, postdoc, as well as PhD student, and because of which I am able to stand before you. This is the recognition which I have received, and take-off message that if you can design nanostructural smart material using the concept of molecular engineering and using bio-based material, you can get multifaceted attribute and engineer such material high potential for different advanced application. Approach is towards the sustainability and minimize the energy consumption as well as waste management, and it uses renewable resources. Thank you very much for your kind patience.
Thank you very much, Professor Karak,
Yes,
for
sir.
sticking exactly to time.
Yes,
So
sir.
exactly 25 minutes, he's finished. So the seminar is open for discussion and questions. Yeah.
Yeah, it was amazing to see that the materials that you design is applicable to almost everything that one can imagine. Now my question is, what is exactly your molecular engineering? Because the active material that you use depends, of course, on the application. Sometimes it is reduced graphene oxide, sometimes it's titanium oxide, which all are familiar material, and I assume your bio-based hyper-benched polymer is the molecular engineering.
Yes,
So I'm just curious to know what specific molecular or macromolecular properties of the polymer that is engineering and that is kind of design. What is the molecular design?
Okay. This is a very good question. Thank you very much for that. If you see, I told you in my presentation that architecture of a polymer has significant contribution in processing as well as performance. So how you are controlling the architecture, say especially this hyperbranch architecture, by using multifunctional, generally we have used AX plus BY approach where X and Y is greater than or equal to 2, without cross-linking the product which is processable, which is soluble, and which can even reprocess, and getting the different multifaceted advanced application targeted property.
So you mean you believe, say, another commercially available polymer, polylactic acid, will not do the job that this polymer is doing?
Yes.
Okay, thank you.
Other questions? I thought I saw someone here this side.
So it was a good presentation. What was the strategy you adopted throughout this work? You have done a lot of reinforcement, how did you control the interfacial interactions within the reinforced systems to modulate the properties?
Thank you. This reinforcing effect or interfacial interaction that's most important for the performance. Now, to get the highest or maximum degree of reinforcement, your interfacial interaction will also be maximum. And for that, if you see, when you functionalize, proper functionalization, which will become the part of your polymer chain, which are present in the nanomaterial, then effect is much higher than without functionalizing it. So how are you functionalizing your nanomaterial to interact with the polymer that govern your interfacial interaction and hence the reinforcement?
Niranjan Garg is a very good presentation.
Please.
By and large, hydroxyapatite is a prominent material for a bone tissue engineering. One of your slides shows that you have suggested for injectable bone tissue engineering. Have you done with this kind of a polymer? If it's so, can you explain once again how it has been compatible with cytotoxicity, etc., especially in the matters connected to structural properties of your polymers?
Yes, thank you. It's a very interesting question. We have done the cytotoxicity, cytocompatibility, as well as that histopathological test. Here actually we have chosen polymer which is not only bio-based but waterborne also. Number two, nanomaterial which we have used, that is derived from the carbohydrate or food product. And the process we have used just heating. So no process no chemicals we have used which can impart some toxicity. Okay. So using that type of material, we have done the experiment, and for formation of semi-solid scaffold inside the body system, we have used 10% gelatin. That is hyperbunch, waterborne polyurethane and carbon dot peptide modified carbon dot nanomaterials.
All right, I think we'll close now and thank Professor Karak once again for a fine
Thank you
presentation.
so much.
The next lecture is from my colleague from Indian Institute of Science. He would deliver the first Kishore Memorial Award lecture. This is Professor Suryasati Bose from the Materials Engineering Department at IISc. His talk is titled quite interestingly, From Trash to Treasure, the key role of vitrimers. So, Professor Bose.
Okay. So good morning, everybody. There is always an added pressure on the speaker for the last talk before lunch. But what I'm trying to do is I'll keep my message short and clear. I didn't say short and sweet because I'm going to touch upon a little bitter topic of plastic pollution. We know that plastic pollution, and we have heard from many speakers in the morning, that it's getting into the food cycle, water, soil, and so on. So we should aggressively practice recycling, and that is the focus of my talk for this morning. And I'm going to introduce a new class of materials called vitrimers, and I'll tell you how it can add a new dimension to the recycling. So before I get there, let me thank SPSI for honoring me for the Professor Kaushal Kishore Memorial Award, and also the organizers for having me here for this conference. So as you can see that upcycling and recycling is some of the terms that we keep hearing related to the circular economy of plastics. But the percentage of recycling is very, very small. India is although doing a good job. You wouldn't see plastic bottles and HDPE oil cans in the landfill these days because they are being picked up and sent for recycling. What is there on the landfill is all single-use plastics, which needs some more attention before it can be disposed of. So sorry about this busy slide, but as you can see, there are tons of reports of plastic pollution. There are more, but there's no place on this slide. So all this are pointing towards one major problem that we are going to face in the coming years. We have already started seeing it. So if you see, there are tons of plastic. So there are tons of plastic in the riverbeds, in the oceans. The recent UN report says there are a lot of plastics in the land. So these are the plastic sheets that are often used to restrict the moisture loss from the soil, and they end up in the soil itself. So all this are hinting at a major problem, and recycling, of course, is one of the solutions, but I'll walk you through some of the recent literature and our own work from IISc to show that vitrimers can also help in recycling plastics in much bigger way. So although India has joined other countries in banning single-use plastics, but if you see the recent reports again, you would see that 3 months down the line, the ban has failed. It only says that there are no alternative materials at the moment. Therefore, we should aggressively practice recycling to end the plastic menace that is in the landfill. So Professor Mishra is here in the audience, and he keeps telling me that the plastics can't swim, they don't have legs, so why are they at the wrong place? So why are they in the oceans and why are they in the river beds? So that's an important point. Why are they at the wrong place? So there should be ways to recycle them rather than disposing of. So I would leave the audience with a very strong statement is don't ban me, but try to manage me better. So banning is of course not a solution because there are no alternative materials. And that's the reason why you see that like many countries, we have failed, right, to strictly impose the ban. So I will take a very nice incident, very interesting incident from Bangalore. So this is our tunnel borer, which is, digging up tunnels for the metro constructions. And then 33 feet below the ground, it has hit a large pile of garbage full of plastics and rubber. So this is how we are managing our plastics. So the work was stalled for about 3 months, clearing up all the blades of this tunnel borer and so on. So some nice initiatives are being taken place by a very famous company called Akshay Kalpa. So what they do is they deliver you milk, and the next day the boy collects back the milk pouches. So they sent it for recycling, and what they do with it, I'm not sure. But it's a good initiative that these things are being collected right at the point of sale so that many new materials can be, many new products can come up from these materials. So when I looked for a lot of statistics, I was a bit confused, although there are tons of statistics, but all of them paint a very grim picture about the recycling. So if you take a look here, 8.3 billion tons of plastic is being produced. Much of it is waste, but a very small number is being recycled, of which there are process losses, and there's only 2% closed loop economy. So which also means that the rest ends up either in the ocean or in the land, and therefore creating a lot of menace. It has also entered the food cycle, and we hear about microplastics these days in our food cycle. So although the statistics is a bit confusing because there are tons of statistics, as I said, but all of them are hinting towards a strategy that needs to be devised as early as possible for recycling of plastics. So if you take a look at the global plastic production here, much of it is used for packaging, and that also contributes the major plastic waste. So packaging is one of the major industry which is contributing to the plastic waste. But if you look at the treatment, much of it ends in the landfill and for incineration, which is actually energy loss. So there is no point incinerating because the amount of energy needed to create plastic, more than that is needed to incinerate and destroy it. So a very small number is being recycled, and these numbers are pretty high in this country, I'm glad to say that, because 30% of our PET and HDPE is being recycled. Other major worlds are actually recycling very less. So we have a very efficient way of recycling PET and HDPE, and which is being recycled in one of these strategies here. So either there is upcycling where they are being 3D printed into useful items, or being recycling, or being downgrading into gasification and pyrolysis, waste to energy, and at the end, if nothing comes through, it goes to the landfill. So if you take a look at our plastic consumption here, much of it is polyolefins, from milk pouches to oil gallons and whatnot. So these are mostly polyolefins that ends up in the landfill. And if you take a look at the packaging material, so they are thinner than 50 microns, so they can't be even recycled. So even more worse are the MLPs, multi-layered plastics, the chips packets, and all the Tetra packs. They have a very little amount of polymer which can't be recycled, and therefore it directly ends up in the landfill. So how to address this? There are only two options at the moment. One is aggressively recycle, or we move towards biodegradable plastics, which we just heard from different speakers this morning. But then with biodegradable plastics, there are other problems. When it ends in the landfill, there are methane emissions. There are some oxo-biodegradable plastics which could lead to microplastics at the end, we are not sure. So therefore, one of the easiest and one of the most efficient route is to recycle aggressively. So now when you try to recycle, either you reduce or reuse in such a way that they can be recycled n number of times so that we cater to the circular economy. So this is a general diagram which explains recycling, and in India it's also followed the same way, that you collect all the raw material, you send it to a cyclone separator. There are also instruments these days which can sort colors from HDPE and PP post-consumer recycled material. then you grind it, then you run it through an extrusion, then you mold it into a different article. However, the dream would be that if you have started with a bottle, why not ending up in bottle again? But in the process of processing, we lose molecular weight, the MFI goes up, and these are some of the issues that needs to be addressed. And I'll tell you in a while that how Vitremus can actually solve this issue of rising MFI and reducing molecular weight. So I'm happy that some of the industries, startups and major giants are actually recycling plastic aggressively, and one of them topping there is Manjushri. And I'll tell you in a while that we just initiated a center of excellence at IISc for plastic upcycling and recycling with generous donation from Manjushri. So now what are Vitremus? So these are a new class of materials which fall somewhere in between thermosets, which are non-recyclable because they have permanent cross-linking, and in between thermoplastics, which can be reshaped and remolded, but they lose properties every time whenever you process them. So these are the materials which rightly sits here, and what they contain is covalent adaptable networks. So these are dynamic chemical bonds, which you can break them during processing, but they can rejoin whenever it is coming out of the extruder. Or you can, if you want to break them again during the molding or post-molding operations, you can do it once again. So they are majorly classified as dissociative cans, as we call them, or associative cans, like for example, the Diels-Alder reaction here. So you break them, at the intermediate stage, there is a loss of integrity, right? Whereas in the case of associative can, like transesterification or disulfide metathesis, you always have a fixed cross-linking density, so the topology doesn't change. So how about taking this chemistry here and adding it to the polyolefins and PET so that you can have a fixed topology even during recycling, and you don't lose the molecular weight. Even if you lose the molecular weight because of beta scission or because of moisture, you can still join the fragments together by these unique chemistry. So Vitremus certainly will have a say here because it will help in recycling plastics, and as you can see that you can recycle them n number of times, thereby getting into the circular economy. So now the question is, how many such covalent adaptable networks can you add to your polymeric system? So since this field is relatively new, there are a lot of literatures coming up. However, what we have understood is the single can all the way up to triple cans, people have used all three. And higher the number of cans, the more quicker is the rearrangement, which means they will quickly rearrange during processing. So they lose the molecular weight and quickly rejoin and join the fragments. So therefore, associative cans, number of cans, if you can introduce in a plastic, you probably could lead to a case where you can recycle them n number of times. So a little bit, let's step back to see that how Vitremus are different from the thermosets. As I said that epoxies and other thermosets, you can't reprocess them, although towards the end of my talk, we'll see that there are also reprocessable epoxies that we have developed, which you can now reshape it. They are no longer thermoset, but I'll come back to that point later. So in the case of thermoset, you have a permanent network, whereas Vitremus shows some stress relaxations. So which means that when you try to process them n number of times, they don't lose their molecular weight the way a general thermoplastic would do. So therefore, in order to not to have a permanent network, so let's introduce some adaptable networks that can break and rejoin during processing so that you can process n number of times. So these are some of the Vitremers that are available in the literature. If you take a look, there are amorphous Vitremers where the topology freezing temperature is more than the TG of the polymer, and here in this case where they are less than the TG of the polymer. So therefore, they can break below or above TG depending upon the chemistry that you choose. So these are some of the examples from the literature. This is an epoxy which is known to be thermoset, but if you see here, this is the same DGEBA, right, glycidyl ether. So this DGEBA can be made into a thermoplastic epoxy by introducing this small chemistry here, which is vanillin and aminophenol, so which forms an imine exchange. So whenever it's going to cross-link, it forms an imine exchange, and you can break this imine exchange whenever you want to. So which means at room temperature, these epoxies behave like a thermoset, but at high temperature, they actually flow like a thermoplastic. So now you have epoxies that are malleable, weldable, and you can keep recycling them a number of times. But the question is whether they give you the same properties as that of a thermoset epoxy, and the answer is yes, because you need to choose the right chemistry here, choose some aromatic compounds that gives imine exchange or siloxane exchange, so that you end up in malleable, weldable epoxies which have similar strength as that of the thermoset epoxies. And if you have to choose between one of the cans, you would choose an associative can so that you freeze the topology, and these epoxies can flow at higher temperature and you can reshape them. So these are some of couple of more examples on epoxy with siloxane exchange. So again, these SiO-Si bonds are dynamic in nature, so which means they can break and rejoin whenever you want to. So these epoxies are again thermoset at room temperature, and you can reprocess them again and again because they flow like a thermoplastic. If you see the number of cycles that these epoxies can now take, so up to the 4th cycle, we don't see much difference in the mechanical properties. So therefore, you don't lose properties as you keep recycling them. Some of them also end up in being transparent. That is how the beauty lies here. So you don't use things that give color to epoxy. So you have epoxies that are transparent and also can be recycled a number of times. So let me move to thermoplastics, because that is where our interest lies in. So these are post-consumer recycled polypropylene. So what you do is you just take maleic anhydride, add some DCP or peroxide, attach this maleic anhydride onto PP by hydrogen abstraction. And now when you add some epoxy to this malleated PP and a zinc catalyst, which is a trans-esterification catalyst, you end up in a dynamic bond, which is a trans-esterification bond here. So therefore, this PP now can be recycled n number of times without losing on the properties, because every time you process, these bonds break, but then when it comes out of the extruder or after post-processing, they again rejoin. So therefore, you can now process them again and again. You can see a small rubbery plateau even in the melt in these kind of Witrimer polypropylene. Same is true with HDP. So I'm talking about PP and olefins because that, if you remember my slide, it contributes to the major packaging waste, contributing polyolefins. So these are all post-consumer recycle HDP. So again, you have epoxy groups attached to this, and you use a diol and you use a catalyst which forms these kind of dynamic bonds so that you can cut and recycle them a number of times. So if you take a look at the stress strain diagram for the virgin HDP and the recycled one, you actually upcycle them by using these kind of chemistries. So these are some of the glimpses of polyolefin literature. There are a couple of more. In the interest of time, I'm not going there. So my interest here is LDP, because even we started working with LDP using the milk pouches. I'll show you in a while. But the same concept of grafting maleic anhydride and using a disulfide metathesis in this case actually gives you an LDP Witrimer. So this disulfide bond breaks above the melting point of LDP around 200, but then they can quickly rejoin. And if you take a look at the stress strain profiles of most of these Witrimer polymers, they can be processed 6 times, 7 times without losing their mechanical properties, because each time you process them, there is the beta scission that may occur during processing. The fragments are rejoined by these kind of simple chemistry. So that was all about polyolefin. As we know that PET also contributes majorly to the plastic waste. So there is only one literature one paper that is in the literature which talks about PET Witrimers using Bistris. It's a small molecule with tons of OH groups. And what it does is it forms a nice cross-linked PET, but these cross-linked are dynamic in nature, which means again they break during the extrusion process, and then you can actually rejoin them, and these can be processed a number of times. So here they have shown compression molding 4 times without losing its transparency and the properties. It was extruded 3 times and injection molded for a couple of times, so without losing much of its properties. So they are again insoluble, because now you have cross-linked them, but if you heat them, they can be made into soluble. You reprecipitate the PET and reuse it. So therefore, Witrimer certainly has an answer to the recycling business. This time, when you're adding these kind of small molecules, you can actually end up in a different kind of PET, which can be recycled a number of times. So if you take a look from the rheology point of view, so if you see the creep resistance for the neat PET increases with increase in temperature, whereas the PET vitrimers have less deformation and less creep, so they don't creep, right? So therefore, the permanent, the temporary crosslinks or the dynamic crosslinks that helps in less creep in the case of PET vitrimers. There is again one study on polycarbonate vitrimers. So again, very cleverly they have used vitrimers to make polycarbonate, introduce dynamic covalent bonds in polycarbonate. So these are the vitrimer polycarbonate you can break, and then you can reprocess them without losing much of its properties. If you see here, this is the end of the life of polycarbonate. You can dissolve, reprecipitate, and use it again to make the part. So this is how polycarbonate can be recycled. So these are some of the literature that I have gathered for my talk today. If you see, this is pristine PBT, which has a very weak strain hardening, and when you add some vitrimers, it shows a very strong hardening. And if you see here polypropylene, this is the virgin polypropylene, and each time you extrude polypropylene, you see an increase in the MFI because there is a lot of chain scission, beta scission happening during the processing stage. So when it happens, then it becomes very difficult to extract a useful item out of this recycled polypropylene. So therefore, if you are adding a vitrimer, you probably would end up in upcycling the properties, or maybe you can at least arrest the loss in the mechanical properties. So that was all about the literature. So let me come to our work in IISc. So we have chosen LDP because this is the company which delivers milk in most of the houses in Bangalore, and our landfills are mostly, plagued with Nandini milk packets. So we thought, let's start with this milk pouch, and it's written LDP, so we were sure, and we characterized that it is LDP and not a mix of LDP and LLDP. So we have chosen 2 bio-based oil, which are non-edible oil sources. So we don't want to hamper the food cycle. So we chose this bio-based, non-edible bio-based oil. So by simple extrusion of these molecules, the next challenge was to extrude them for very little time, because the residence time in industries is very, very short, 3.5 to 4 minutes, right? So therefore, we need to cut down on the time. We can't process them for very long, which we usually do in a lab scale extruder. So we wanted to keep the time short. So once you mix all these 3, the maleic anhydride groups here will attack onto LDP, and this will open and form a trans-esterification type of reaction. And this can be accelerated by using a zinc catalyst, and this is how you get out of the extruder. You chop it and then you mold it, and these are 7th cycle of LDP, and what we see is it doesn't lose its property even after 7 cycles. So if you just take an LDP milk pouch and start recycling it for 7 times, after 3 or 4 times you would see that the mechanical properties is so low that you can't even use it, it can't be even molded. So our materials can be now compression molded, and also in this case injection molded, you can see here. So what we have done here is we have added one more compound here, which is silyl ether. So if you add these 3, you get a single covalent adaptable network, single CAN, but if you add this, you get a dual CAN, and we wanted to see that if you introduce 2 covalent adaptable networks, what best you can make out of it. So we are again at the 3rd and the 7th cycle, and we see that the properties don't deteriorate, at least the yield stress doesn't deteriorate, but there is a loss in the elongation at break. So they become a little brittle, but they still have properties that can go in various applications. So we are able to mold them even after the 7th cycle, so which is good, which tells us about that they didn't lose their properties during 7th cycle of recycling. So these are some of the examples that I got very recently. Yesterday, these were in the newspaper, where a startup from Cochin actually started making this interlock bricks from recycled plastics, and also these furnitures, which is now sitting in CPET Kochi campus. So these are the blocks which are made from milk pouches. So they have been able to recycle the milk pouches to make these things. But I'm not sure whether they are vitrimers, because if they are not vitrimers, you will not be able to recycle them back. You would lose the properties. So our idea is to have some products, something like this, where we can actually recycle them back to make the same furniture or the same interlock bricks. So this is the Center of Excellence I was talking about, which was conceived very recently, last week, and we want to call it as Reborn, which is reuse and beyond recycling. So this came from generous funding from Manjushri. So you see all these products, these are all, you name the product and Manjushri actually packages it for you. And what we are trying to do with them is we are trying to close this loop using Vitrimers. So they are supplying us post-consumer recycled plastic. So every day morning, tons of HDP gallons come to their factory. They shred it, clean, wash it, delabel them, and send it to us. So we extrude in batch scale, but they can extrude it in bulk scale. And what we are going to do is they're going to make paint veil out of these plastics. So currently they are making it, but the dosage for recycled material here is only 8%. And with this center of excellence, the idea is to go 100% post-consumer recycled material. So all the HDP gallons, if it can be converted into a paint bucket or paint veil, that is how we can reduce the plastic waste in the recycle. So these are some of the opportunities that are possible, and I would leave some challenges for you to think about. Most of the Vitrimers are still brittle in the case of PET and olefins, so this is one of the major challenge. Some of these Vitrimers also contain toxic catalysts like DCP and others, so we need to find out ways to use a mild catalyst. Although they are dynamic reversible, the thermal stability has to be checked, and therefore they can have a lot of applications for different products. So with that, I would like to end my talk. Thanks for the patience hearing. Thank you.
Thank you very much, Suryo, for keeping to time and also presenting an excellent overview of the challenges and possible opportunities. So I open the seminar for questions, and I'm sure there'll be many. Yeah.
Okay, thanks Dr. Surya, my good friend, for bringing this pertinent concern. In fact, Vitrimers are coming up in a large scale, and it's not a question really. And when you said that we are not really sure that there is some Vitrimer in there or not, when you are using this triglyceride with your LDPE, so what can be done is you can simply run a stress relaxation trace, and if that follows a Maxwellian pattern, then of course there is some dynamic linkages present in there.
Right. So for our work, we know, because we have added non-edible oil sources, so we know that it's a Vitrimer with a nice stress relaxation, a rubbery plateau. But from the products that are there in the market, we are not very sure that when they are recycling, whether they are really using Vitrimers or not. Yeah.
So actually the work is very interesting.
Thank you.
And I have just wondering, I mean, next to polyolefins, our problem is on electronic materials, especially ABS and so on.
Right.
I mean, is it the similar kind of chemistry will work there as well?
Yes, because a lot of electronic waste has polycarbonate, right? And there's only one literature that we have seen where polycarbonate is being vitrified to recycle it. So we have been talking with SABIC, because they have polycarbonate ABS car bumpers and so on, and they wanted to recycle PC ABS blends. So the same concept of Vitrimers, we just started working with SABIC on that. So the same concept can be extended for polycarbonate as well.
So, okay, what about ABS?
ABS as well. ABS as well.
Thank you.
Yeah, go ahead.
Thanks a lot
Hi,
for
Samir.
a nice talk. And I think this is a growing area, and we should, as a polymer community, we should look at it. I have a few questions about polyolefin Vitrimers.
Yes.
You showed, maybe it was a literature report, where you have been able to activate a CH bond. CH2 is not an easy chemistry to activate a CH bond. There is a whole lot of group working on CH activation. So I don't know how you could activate a CH bond and get a CH bond activated to make a CC bond and then make a Vitrimer.
Right.
That's the first part, to get a CH bond activated, functionalized, then add a Vitrimer to it. The second one is, after making these Vitrimers, let's say you recycle 6 times, 7 times or so on. So what happens at the end of life? So all these HTP is still going to go through something, or are you going to break it down, bring it back as monomer?
So breaking down, let me answer your second question first. So breaking down is a lot of energy being consumed there, because the energy that is consumed to make HDPE, if you take into account that, there's a lot more energy you need to break it. So certainly what we are planning is these HDPE should enter the circular economy, so you should be able to recycle them n number of times. So we are at 7th cycle, but under the COE we are trying to get and see how long we can recycle HDP. So coming back to your first question, so we are using dicumyl peroxide. So these peroxides actually create a free radical, and that is how through the H abstraction you attach a maleic anhydride onto an polyolefin chain. So that's a known method. People have been using this technique for grafting maleic anhydride onto polypropylene. So we borrowed the same concept. So now the same maleic anhydride you can use for trans-esterification reactions, right? You can also use a permanent cross-linking by bringing in an amine source to it. That is how epoxies are being cross-linked. But for olefins, that is a major challenge, that the first step is to get a maleiated or an epoxidized polypropylene or HDP.
Any other questions? Yeah, go ahead.
Yeah. Just two questions.
Yes.
So, whenever we process any polyesters, industrially when they do extrusion, definitely they add epoxides to reinforce it. Correct? So, every time we reprocess it, we'll add epoxide to reinforce it, again to get the mechanical property back.
To PET bottles, you mean?
Anything, you only make a reactive blendings, anything you do,
Yes.
when they do the extrusion, they definitely add epoxides.
Right.
So, in order to maintain the mechanical properties, some of the approach which you showed in from the literature or some of the work which is I think, you never go back to monomers. You basically break some oligomers, again add some epoxy, reinforce it. Maybe few times you can recycle it. But that does not mean that you are actually breaking the polymer, going back to monomer, again you redoing the polymer. So in terms of ideal wet trimmers, which are what I'm talking about, you should be able to go back to the monomer stage. So one should be able to rebuild the polymer or whatever you want. So I have little bit different opinion on the wet trimmer examples which are cited by you or shown by you. In my opinion, they are not the best reprocessable in my view, because you should go back the imine chemistry which you are talking about. Yes, you can completely cleave, you can go back to monomers, but not on the other approach. So that's, you can comment on that one.
Sure.
Second thing, that you are talking about the trans-esterification between your polyolefins with some kind of you have some ester oils which are adding that. How a polyolefin undergo a trans-esterification with your oil molecule, which I don't understand.
Right.
Can you explain on these 2 points?
So if you remember that slide, so there was maleiated oils. They were not just the oil. So these are maleiated oils. And these maleic anhydride groups, by using a simple peroxide catalyst, will transfer onto LDP. Right? Just like how you graft maleic anhydride onto polyolefins inside an extruder. So you take maleic anhydride, you take polyolefin, you add some peroxide catalyst like DCP, for example, or BPO. Yes. So those are maleiated oils. So now the double bond in the maleic anhydride will actually open up in presence of DCP, and because of H abstraction, they will graft onto your polyolefin. So now once it is grafted, you have the epoxy groups that can attack on the maleic anhydride groups, and therefore you create. Coming back to your first question, so the definition of vitrimers is not really going to the monomers. So what happens in PET, in the case of PET processing, so you see some chain scission, right? So the molecular weight goes down, but then in the case of, as you said, that they add epoxy to basically join the fragments. So we don't go back to the monomer, because the time it spends in extruder is very, very short. It's about 3 to 3.5 minutes is what we have seen. So actually it doesn't degrade the PET to that extent that it goes back to the monomers, but it certainly cleaves many of the chains, and these vitrimers can help in joining these fragments.
Sir, I would like to ask that you are using trans-esterification for synthesizing this vitrimer. So trans-esterification has a problem with that they can get decomposed in acid as well as base. So let's say you are using it to as a solvent storage, chloroform, or as a base bath solution. So wouldn't it decompose the material itself?
You mean the catalyst?
No, sir. Trans-esterification, it can be catalyzed by acid as well as base, na?
So what we are using here is a zinc acetate trans-esterification catalyst. So that will actually make the process much quicker. So there are literature where they have avoided the trans-esterification catalyst. If you remember, I have shown you one slide with bistress. So they can auto-catalyze PET, right? So we don't have...
Wouldn't it decompose, like, let's say I am storing a base bath. I made a base bath solution and added it to the material that you have made it. Now, wouldn't it decompose the material, because trans-esterification starts breaking up because there is base in it? like is it a limitation or like it won't happen?
I mean, people have to look at more closely in that case, whether for certain application, whether it is not possible or not. But for the literature that we have, or what we see for the PET, for the trans-esterification, they didn't report any problem as such. But maybe it is, if it is a very specific problem, as you said, that if you want to store acid or base, what would happen to that container has to be closely looked into.
Hello.
Yeah.
So I was wondering that how long it takes to undergo complete stress relaxation for this vitremer.
Okay, so the graphs that are there is not long. So if you see, they are about 15-20 minutes is what you see, right?
So
the stress relaxation, yeah.
But you show the extrusion molding, but their polymer stage.
Oh, you mean how long was the processing done?
Yeah.
Okay, so what we have done is for 5 minutes, but in industry, what we have seen is the residence time is very short, right? So it is about 3 to 3.5 minutes. So the trans-esterification reactions doesn't happen that quickly. And therefore, these products have to be annealed separately outside the extruder for a very long time. So that is one of the problems with trans-esterification catalyst. And we want to move away from trans-esterification and go to disulfide metathesis or acetal exchange or silyl ether exchange, so that these reactions are quite quick. Trans-esterification takes time. So therefore, most of the literature talk about post-curing of these materials.
All right, I'm sure there are many more questions, and Surjo will be here during the conference, and you can approach him and discuss this during the lunch and other breaks that we have. So with that, let me thank Surjo again, once again, for a fantastic presentation. And I'd like to thank all the speakers of the session for not only keeping the time, but delivering really outstanding talks during the first session. And thank you all, and I think we'll break for, I'm sorry.
Thank you, Professor Ramakrishnan, for chairing the session. I have a few announcements. Please don't leave, because you might need to know this. One is that the lunch is outside once you leave the building on the right-hand side. The second one is we have been talking about sustainability, so we would prefer not to use too many plastic bottles. Hold on to your bottle. There are a lot of refillable, like where you can refill the water dispensers, and we have provided a water bottle in your kit, registration kit. You can use it from tomorrow after washing it, maybe. That's one thing. There is some announcement about the poster. There is some change in the poster. I'll just read it out. Categories A, F, and H will present on 2nd of November from 5:30 to 7 p.m. That's today. And categories B, C, D, and G will present on 4th of November from 12:30 p.m. to 12:15 p.m. And the last announcement is that please wear this tag when you're going for lunch. That will help the people to identify that we are from this conference. Okay? Thank you, and hope you have a great time.
Yeah, you should.
Hello. Good afternoon, everyone, and welcome to the post-lunch session, where we have 3 talks. I'm going to request Dr. Ashok Mishra to chair this session. Professor Mishra is currently the Nasi Distinguished Professor at IISc Bangalore, and I'll request him to conduct the proceedings of the session. Thank you.
Hello, good afternoon to all of you. Now that you have had a good lunch, we are ready for the next session. So in this session, we have three talks. There are 2 endowment talks, and 1 is a plenary talk. So the first lecture today afternoon is the Dr. S. Shivram Endowment Lecture, and this will be given by Dr. Richard Hogenboom. He is a full professor at Ghent University and heading the supramolecular chemistry group. And his talk will be in supramolecular polymer materials. So, and all the details are given in the booklet. So without any further ado, let's start the lecture. The lecture will be 25 minutes and we'll have 5 minutes for question answers. 25 minutes, right? Oh, this is 45-minute lecture, so 40 minutes and 5 minutes for question answer.
Okay, thank you very much for the kind introduction, and I would like to start with thanking the organizers for the honor of asking me to give this endowment lecture today and for giving me the chance to take the stage today. And what I will try to do in the next 40 minutes roughly is to share some of the work we've been doing on supramolecular polymer materials, which is one of the 3 main research areas in my research group. But before doing that, I also have, of course, a quick look at the career of Dr. Sivaram, which is very impressive and who has been really very important for establishing polymer science in India. And I also noticed that he has had a major impact in teaching many of the younger generation professors that are here in the audience that are already becoming more and more established. So congratulations on this career achievements. Well, besides that, I also would like to announce that in the background we have been working on a special issue for European Polymer Journal. So I'm editor-in-chief for European Polymer Journal, which received a new impact factor of, let me see if my pointer will work. Yeah, it's there. Yes, so a new impact factor of, this is difficult, 5.5 last year. And in this special issue, we've invited people that have been impacted by the mentorship of Dr. Sivaram to contribute to this special issue. This was not my idea, so I have to thank the guest editors, so Dr. Nikhil Singha and Boje Gaut, who initiated this special issue, and we hope that it will be published soon with
well, just over 20 contributions from scientists from all over the world. Now, talking from all over the world, I'm coming from Ghent University in Belgium. This is how we like to see the world in Europe, with Europe in the center. I know many different places in the world, they see the map different. But as you can see in this map, you can see here in the middle of Europe, Belgium, Ghent, very close to Brussels. And if you zoom in, you will find that this is a very beautiful medieval city with an old harbor, an old castle in the city center, and of course the famous Belgian beers and chocolate. So if you come to Europe, feel free to contact me and I would be happy to host you in Ghent. If you come to the chemistry building, it's not as beautiful as the buildings over here. It's quite an old building that we have. But inside this old building, we have state-of-the-art facilities and almost all the equipment you can dream of for organic synthesis, polymer synthesis, and polymer materials characterization. So what I will talk about today are smart polymer materials, and I will share some of our ideas on how to get to smart polymer materials. But before doing that, just a very schematic view of what I mean with a smart polymer material. So what we try to develop is a polymer material. It can be a solution, can be a bulk material, and that under influences of an external trigger or an external event, change in the environmental parameters, will undergo a change in its properties. And the change in properties can be very basic. It can be a change in color. Then you can think about sensor applications. It can be a change in shape. Then you can think about actuators, molecular muscles, or it can be a demixing phase transition. So if you can control a polymer to be soluble or insoluble, we are looking at this, for example, for drug delivery applications. Now, the types of triggers that induce these changes can be manifold, and that can range from mechanical force, changes in pH or temperature of solution. It can be external radiation, magnetism, or the presence of certain analytes that induce these changes in the polymer materials. Now, making smart polymer materials is not something that synthetic chemists have come up with. This is actually already omnipresent in the world around us. If you look at biological systems, this is full of smart materials, nature's smart materials. And for me, most of these smart polymer materials are based in nature on proteins. And as we're here in a polymer conference, I would like to remind you that a protein simply is a polymer structure. It's a perfectly defined polymer structure that through the combination of certain order of the amino acids is able to fold through the use of supramolecular interactions to get additional smart functionalities. And some examples of these smart proteins in nature are the ribosome, so that's a protein that is able to read out RNA to make new proteins. You have these actin filaments, so they are able to give viscosity and strength to cell materials. And you have this very exotic, beautiful protein, so this is a motor protein that walks over an actin filament to bring a vesicle from one side of the cell to the other. So nature is able to do all of this, all this smart function, based on polymer materials that are based on only around 20 different monomers, the amino acids. So very limited toolbox, but by the combination of chemical structure and supramolecular interaction, you can get all the function in nature. Now, as polymer chemist, I would like to get my inspiration from these systems, but not limit myself to 20 monomers. So as chemist, I can use hundreds, thousands of different monomers. So I believe that in the end, by taking inspiration from these systems, we should be able to develop the next generation smart materials that might even outperform nature because we're not limited to a certain set of monomers. Now, we of course need some generations of polymer science to achieve this because nature took a couple of billion years to develop this. I will still have well, maybe 30 years left to develop this in the lab. So we really need to team up with teams of polymer scientists to achieve this, to develop these next generation smart polymer materials. So based on this philosophy, in my research group, we have three main research teams. But what they have in common is that we try to do molecular engineering to design functional materials. And what I mean with that is that we try to understand the needs for a certain application or a certain property that we like to get in the material, and then we try to retro-design the monomers and the building blocks that we need to get to these properties. So we really start always from the organic chemistry to make the building blocks. And the three topics that we work on are polyoxazolines, so this I will not really touch upon today. So polyoxazolines are a synthetic class of polyamides. You see the structure over here, so this is ethyloxazolin. This can be made by living cationic ring opening polymerization, and these polymers have very beneficial properties for biomedical applications, so they can suppress interactions with proteins and cells without inducing an immune response. So that's the main property why polyethylene glycol is so important in medical applications. These polyoxazolines have the same properties, but they can be tuned and functionalized much more than polyethylene oxide. So we believe this is an important area for these polymers. Now, then we also work on more application-driven responsive polymer systems. So these are polymers that are intrinsically responsive to either pH or temperature and undergo a phase transition. And we often functionalize those with dye molecules to make sensor materials. And examples of sensor materials include here nanofibers to have a very high surface area, functionalized with dyes that we can use for monitoring of food spoilage in food packaging to prevent food waste, but also in bread analysis to, through the bread, see if a patient has a certain disease or not. So you can monitor outside the body if a certain disease is manifested inside the body. We also make some pH-degradable polymers for drug delivery applications. But the main topic of today will actually be about supramolecular polymers and supramolecular polymer materials, which actually is the most fundamental research area in my group, where we really try to develop new concepts and try to achieve things that were not known yet, that materials and polymer materials can do that. So that's what I said. I will have a short introduction on thermoresponsive polymers, more specifically LCST polymers. Then I will show you how we have taken thermoresponsive polymers to combine them with supramolecular interactions to make temperature sensors with a memory function. Then I will show you how we have brought this to hydrogels to make actuators and sensors with not only a temperature memory but also a time memory. And in the end, I will show some work on hydrogels that are able to dissipate energy. Okay, so let's start with the thermoresponsive polymers, and what I will be talking about today mostly are LCST polymers, so polymers that have a lower critical solution temperature. And that means that at a low temperature, these polymers are nicely solubilized in water, so you have a clear solution of the polymer in water. And then if you increase the temperature, you increase the entropy factor in the Gibbs-free energy equation, and it becomes entropically unfavorable for the water molecules to hydrate the polymer, and therefore the water goes back to the bulk water. You have a less hydrated polymer left, and that coagulates and precipitates, giving you a clouding of the solution. Now, typically, these LCST polymers have a phase diagram that looks like this. This is a very schematical representation. But at low temperature, the solution of a polymer in water is present in a single phase, and then if you increase temperature, you go to a two-phase, where the system phase separates in a low polymer concentration phase and a high polymer concentration phase that is usually dispersed in the aqueous phase. Now, some definitions. If you want to know the LCST and report the lower critical solution temperature of a polymer, you need to determine the entire phase diagram to find the minimum of the phase diagram. So what we usually do, we measure clouding at one fixed concentration, and then we report the cloud point temperature at a specific concentration. Now, the most famous polymer in this area is poly-N-isopropyl acrylamide, which has a cloud point or an LCST, the phase diagram has been determined, around 32 degrees centigrade. But if you look in detail at the heating and cooling cycles, you can find that polynipam will have a small hysteresis in between the heating and the cooling cycles. So if you increase temperature, the polymer phase separates around 32 degrees, and then if you heat further, it remains precipitated, and then if you cool down, it will only redissolve around 30, sometimes 28 degrees centigrade. So there's a small window of hysteresis, which might be problematic for certain applications. And this hysteresis is ascribed to the presence of the secondary amide in the structure, which gives very strong hydrogen bonding in the high polymer concentration phase, which makes it more difficult to redissolve the polymer upon cooling. Also, the glass transition temperature of NIPAM is around 200 degrees, so the dispersed high concentration phase is actually vitrified and is in the glassy phase, making it more difficult to dissolve. So when we entered this area about 10 years ago, we were looking at the polyoxazolin. So you see here the polyethyloxazolin, and the LCST was known to be around 60 degrees centigrade. And we started playing with this side chain of the polyoxazolin. And you can see that if we go to isopropyl, cyclopropyl, and N-propyl, we gradually lower the LCST of these polymers. And the idea that we had is to look more carefully at the hysteresis between heating and cooling, because the absence of a secondary amide and the introduction of a tertiary amide should in theory lead to a much more reversible phase transition without hysteresis. So we focused on combinations of polyethyloxazolin and polypropyloxazolin. Initially we made polymers with different chain lengths, so you see here the number average molecular weight versus monomer to initiator ratio in the polymerization mixture. And then what you see is that for the poly-N-propyloxazolin, for very short polymers, we see a decrease in cloud point transition temperature, which stabilizes after roughly 50 repeat units. So for the short oligomers, these are end group effects that make the polymer more hydrophilic if it's shorter. And for the polyethyloxazolin, we don't have a cloud point for 50 repeat units. This only shows with 100, and then you see a much stronger decrease in cloud point with increasing chain length because of the more and more important interpolymer interactions. And then we focused on this area of polymers with 50 to 150 repeat units and compositions between pure propyloxazolin and pure ethyloxazolin. And we made a small library of polymers that you see here. So polymers with 50 repeat units, 100 and 150, and compositions ranging from pure ethyloxazolin to pure propyloxazolin in steps of 10 mol% in between. So we made all the polymers, we looked at the cloud point transition temperatures. You can see we can span the entire range from around 25 degrees to polymers that are fully soluble, depending on chain length and composition. And we could predict these cloud point temperatures within the boundaries of the library within 1 degree centigrade using this formula, where you can clearly see this is an empirical formula. So we didn't model it, but we just did an empirical fitting of the data that worked pretty well. Now, if you then look at the hysteresis, the most important point that I wanted to make is that you can see that for these polyoxazolin copolymers, we can make polymers that have no hysteresis between the heating curve, so that's the closed symbols, and the cooling curve, the open symbols. So we have exactly the same transition upon heating and cooling. There's no hysteresis. So these materials look more promising than polynipam in case you have you want a very accurate reversibility in the system. But as said, this was just my introduction to show you what most of the scientists in the area of LCST polymers were doing 10 years ago, trying to make new polymers with very low hysteresis for medical applications. So at that point, we asked ourselves the question, well, why should we always focus on trying to have very low hysteresis? Why don't we try to aim and design a polymer system which has a very large hysteresis? So if you can tailor the hysteresis that upon heating, the phase transition takes place at 40 degrees, upon cooling it takes place at 20 degrees, the area in the middle, you have a memory system where you know whether the system was heated to 30 or cooled to 30. And to do that, we teamed up with Patrice Loisel in the University of Lille to combine LCST polymers with supramolecular host gas chemistry. So we designed a polynipam, which in the side chain has this dialkoxynephthalene. That's an electron-rich gas molecule that can be encapsulated in this so-called blue box host molecule. So this host molecule was introduced by Sir Fraser Stoddart, has 4 cationic charges, very electron deficient, and it likes to form host gas complexes with the electron-rich gas, the dialkoxynephthalene. And the idea that we had is that if we take this NIPAM with the hydrophobic gas molecules, the hydrophobic gas molecules lower the cloud point transition temperature, but then upon complexation with the charged host, we actually make the polymer much more hydrophilic, and in that way we get an increase in the cloud point transition temperature. And what we hoped was that if this polymer would precipitate, then maybe the host gas complexation is lost, and if that is lost, then the phase separation at high temperature is the phase separation of the complex polymer, while the redissolution at low temperature is the redissolution of the non-complex polymer. And if that would work, we would have a strong hysteresis between heating and cooling. Well, we determined the association constant for binding. This is around 10 to the 4, so quite a strong host-gas association. So this is then the concept that we proposed, and that is that at low temperature, we have the polymer host-gas complexation. Then if we increase temperature, we still have the host-gas complex until the phase transition temperature of this complex polymer. Then we phase separate the polymer. Well, the charged host doesn't like to be in the phase separated dehydrated polymer, so this would be released into the aqueous solution. And then upon cooling, the redissolution of this non-complex polymer will only happen at much lower temperature, and then once it dissolves, it immediately forms the host gas complex again. Now, that is actually is the case is shown over here. So this is a turbidimetry experiment showing the turbidity of the solution. And if we have this host gas complex polymer in solution, it shows this strong purple color. That's the purple color of the host gas donor acceptor complex. And then upon heating in the red curve, you see that around, this is around 30 degrees, we have the phase separation, and then we get an opaque solution, no light transmits, and we have this white phase separated solution. So the white color already indicates that we have lost the host gas complex. Then upon cooling, we get a phase separated state, and only around 25 degrees the polymer redissolves. And at that point, we have the non-complex polymer that redissolves, and you see we have designed this hysteresis window, and we were hoping that in the middle here, we can do some sensors with memory function. So this is the temperature in the middle, so the 25 degrees here, and we hypothesized that if we heat the solution to 25, the polymer should be soluble, should be purple, clear solution. Then if we heat it to 40 and we cool it back to 25, exactly the same polymer solution will be white and opaque. And then we have our memory function, because by looking at the state of the polymer solution, we know if it was heated. Hours, the solution that was heated to 40 and cooled to 25 is completely opaque. After 10 hours, the solution that was this was heated and cooled to 25, this was heated to 25. After 10 hours, we still have 70% transmittance, so you see a slight fading of the color, but still very clearly to distinguish that this was not heated beyond the transition temperature. And this we were then lucky enough to feature on the cover of Angewand some years ago. Okay, so with that concept in mind, we wanted to move towards actuators and molecular muscles. But to make a molecular muscle, you shouldn't look at the phase transition of an individual polymer in solution. You have to transform this to the macroscopic state. And to do that, we turned our attention towards hydrogels. So we went from the solution to the hydrogels. Well, that's relatively easy to do synthetically. So you take a hydrophilic monomer, dimethyl acrylamide, you combine it with the guest functional acrylamide monomer, and then you add a bisacrylamide as crosslinker, and then by radical polymerization, you can make a cross-linked hydrogel, so covalently cross-linked, having the supramolecular guest units in the structure incorporated. So this is what the hydrogel look like when we prepare it. So it's just a white transparent piece of hydrogel swollen in water. And if we add the supramolecular host, what we see is on the one hand the strong purple coloration for host gas complexation, but on the other hand also the strong swelling of the hydrogel, because by host gas complexation we introduced a lot of charges, the cationic charges of the host, and we sealed the hydrophobic side chains of the guest, the dialkoxynephthalene group. So we both get a colored output and we get swelling of the material. You can control the amount of swelling by controlling the amount of host, the blue box that you add. And to better understand the cause of the swelling, we looked at some reference experiments. So this is first the hydrogel without guest. If you then add the host, nothing really happens to the hydrogel. This is the hydrogel with the guest. And then if you add the host, you see a lot of swelling. But if you add both the host and some salt, some sodium chloride, you see that you completely suppress the swelling, which indicates that the swelling is actually due to charge repulsion of the host molecules that are involved in the host gas complexation. Now, you can also control the degree of swelling by the amount of hydrophobic gas that you add. So the more gas that you add in the native state non-complex, we see less and less swelling because we have more hydrophobic groups. And upon complexation, we see more and more swelling because we introduce more and more of the cationic host molecules. And then the next concept what we wanted to achieve is we had the dream of making a hydrogel that if you heat it a little bit, that it will start swelling a lot. So usually hydrogels, if you heat them up, they start shrinking because of the higher chain dynamics. And we were thinking to make the reversed system, where by increasing temperature, we get a strong swelling of the hydrogel. And to do that, we came up with a three-component system. So the first component is the covalent hydrogel with the supramolecular gas units. The second component is the blue box host, so the charged host molecule. And the third component that we add is a polynipam with a tetrathiafulvalene gas at the end group. And the tetrathiafulvalene, you see this here, is an even more electron-rich gas than the dialkoxynephthalene. So if you have both a naphthalene and a TTF molecule present with the blue box, you get preferential complexation between the TTF and the blue box. So the blue box is not available to complex with the hydrogel. Now, the polymer we choose is poly-N-isopropyl acrylamide, a thermoresponsive polymer. So if we increase the temperature above the cloud point of the NIPAM will collapse and you will release the blue box because the blue box is not included in the phase-separated NIPAM. And then if you release the blue box, it goes into the hydrogel, and then by heating, you have the ability to get the swelling and coloration of the hydrogel. Now, of course, it's a nice concept on paper. We have to prove this in the laboratory. So what you see here is the first experiment we did for competitive binding. So this is a fully complex hydrogel with the blue box host. And then we added the polynipam with the TTF at low temperature. And what we saw in time is that the blue box diffuses out of the hydrogel to form the complex with the TTF in the surrounding solution. So that's shown over here. We start with the purple hydrogel, we add the TTF polynipam, and we end up with a green solution covering a colorless hydrogel. So the complex between TTF and the blue box is green. So this was also confirmed then by UV-vis spectroscopy. Now then we looked at the reversed effect. So having the hydrogel surrounded by a solution of polynipam with the complexation of the TTF and the blue box host, and then increasing the temperature to release the blue box and get the complexation of the hydrogel. So also here the pictures show clearly that this happens. So we have here the hydrogel non-complexed, the green solution, and then after heating we have a clear solution and a purple hydrogel. Now, for the ones of you that have a clear eye, you can see the time of this UV-vis experiment, and you can see that it actually takes 18 hours to get the full diffusion of the blue box into the hydrogel. So it's a very slow process. So the switching works, the heating-induced swelling works, but it's a very slow process because it's diffusion limited. So today, I have somebody in my group that is now working on trying to make porous hydrogels to accelerate this process. Nonetheless, we've been able to show that we can do this heating-induced swelling. Well, this is a reference experiment where we start with the complex hydrogel. We don't have the NIPAM with the TTF, so just the complex hydrogel. And then if you increase temperature, you see the expected behavior namely the shrinking of the hydrogel. If we do the same in presence of the TTF polynipam, at low temperature we have the small hydrogel, non-complex. Increasing the temperature a little bit above the cloud point gives you the swelling and coloration, and cooling goes back then to the non-complex hydrogel. So we see here this very clear reversible switching of hydrogel swelling in the, well, counterintuitive way with heating-induced swelling. Okay, so this brings me then to something more recent. So this is not yet published, but the manuscript has been submitted, and it's actually connected to the observation of the very slow diffusion processes. So what we wanted to use this slow diffusion for is to make a memory that actually records the time of heating at a certain temperature. So for that we replaced the hydrogel from the dimethyl-acrylamide to a polynipam hydrogel, so a thermoresponsive hydrogel. And then upon heating, this hydrogel itself collapses, and you get diffusion of the blue box away from the hydrogel. But the extent of diffusion of the blue box is limited by the time, so how much time do you give for diffusion, but also for the temperature that you heat it at, because the temperature controls the extent of dehydration of the hydrogel. So if you have very strong dehydration, then your hydrogel will collapse, but it will collapse very quickly, and all the blue box is entrapped inside the collapsed hydrogel. So it will not be lost and released to the surroundings. On the other hand, if you would heat just above the cloud point, then the polymer collapses, it's dehydrated only a little bit, and you get more efficient diffusion of the blue box away from the hydrogel. So as said, the synthesis is very similar. We replace the monomers, the dimethyl-acrylamide, by the N-isopropyl acrylamide to make this time memory function hydrogel. So this is then how it works. So we have the hydrogel, we heat it to different temperatures, we wait for different times, and afterwards we recover the hydrogel, the collapsed hydrogel, from the solution, and we let it reswell at low temperature in water to see how much it can be reswollen. And the extent of reswelling is a measure for the amount of lost blue box, which is a measure for the amount of decomplexation, and that can be correlated to the time that it was heated to a certain temperature. So this is to show that it works. So this is the original hydrogel with the amount of swelling. And then we see here heating at different temperatures and different times. And you can see that if we have a temperature just above the cloud point for a long time, we get much less swelling because we get a lot of decomplexation. The intermediate temperature and time, we get intermediate decomplexation and swelling. And high temperature, short time, we get a very quick collapse. We entrap all the hosts in the hydrogel, and we retain a lot of swelling capability. And this is then the decomplexation versus time curve at different temperatures, showing you that for most temperatures we have a relative good correlation between the amount of decomplexation and the time that the hydrogel was exposed to a certain temperature. So here we have now a memory function for time based on the diffusion kinetics of the release of the blue box from the hydrogel samples. Okay, and then I will switch gears a little bit, and I will switch gears to talk about very strong and very tough hydrogels that are able to dissipate energy. And tough and strong hydrogels that dissipate energy is something that we all have inside our bodies if you think of cartilage. If you think, for example, on the knee, there's a lot of cartilage that is able to absorb a lot of energy to make sure we don't damage when we walk. And to make hydrogels that are very strong and that have this energy dissipation capacity is actually very difficult. And in recent years, there are some beautiful examples from the group of Gong who introduced the dual network hydrogels, and they showed that if you have one loosely cross-linked swollen hydrogel, you combine it with a dense second network, you can get one sacrificial network that then dissipates the energy. Now, we were aiming to make strong and tough hydrogels from a single network hydrogel, so without having to do all the complex synthesis of a dual network hydrogel. And for that, we stumbled across this polymer. It's called polyisopropenyl oxazolin. So it's based on an oxazoline monomer with a double bond on the 2 position. And this monomer you cannot polymerize cationically, but you can polymerize it through the vinyl group to make this all-carbon backbone and having this oxazoline side chain. And these polymers, these Pipox polymers, are very hydrophilic. They have been shown to be non-cytotoxic and biocompatible. And actually, to my surprise, they're actually quite stable in water. So in water, demineralized water, or phosphate buffered saline, these polymers are stable for weeks or months, and they do not hydrolyze. So that was quite surprising for me. Obviously, in acidic conditions, these polymers are not stable because you protonate the oxazoline and they will cross-link. But the reason why we're interested in the Pipox is that it's very easy to modify the oxazoline side chain. So if you take the Pipox, you mix it with a carboxylic acid, then you get a proton exchange, you get the oxazolinium and the carboxylate, and upon increasing temperature, the carboxylate attacks the oxazolinium, and you make here this ester-amide side chain. So you're actually making a polymetacrylamide which has this ester side chain, and with the R group we can control the functionality of this polymer. And we've been using this for all kinds of applications, going from LCFT polymers, going to light harvesting system and sensors by introducing dyes in the sites, carboxylic acid. You heat it up to 100 degrees for a couple of hours, and you end up with a hydrogel as shown over here in these pictures. So these are the swollen hydrogels. This one has less cross-linker, this one has more cross-linker, so you can control the swelling properties. And by the R group in the dye acid, you can control the properties of the hydrogels that you're forming. And the hydrogels that we were making were again supramolecular hydrogels, where we've now used a pillararene host as the cross-linker for the polyisopropenyl oxazoline. So this is a pillararene with 4 dimethoxy substituted benzene rings and 1 functional dialkoxybenzene, where the R groups introduce the acid functionality. Well, this cross-linking, the hydrogel formation, cannot be done in water anymore because the pillararene is not water soluble. So we do this in DMF at 100 degrees, and then we do a solvent exchange to get the final hydrogels. And then we make here a supramolecular hydrogel, and the degree of cross-linking we can control by the amount of pillararene that we add. So you see that the amount of cross-linker also controls the swelling degree, so we can have materials that swell 600% compared to the solid state. If you add more cross-linker, they swell less, obviously. And these hydrogels are also still capable of supramolecular host-gas interactions. So here you see the encapsulation of this paraquat, the dimethyl viologen, inside these hydrogels. And then our big surprise came, and that was when we looked at the mechanical properties of these pillararene cross-linked hydrogels. So what you see here is the stress-strain curve based on compression. So we take the hydrogel and we just compress it, and we measure the force needed to compress it. And what we saw here is that we easily reach megapascal range strengths, which is very tough for a single network hydrogel. So there's not many examples of single network hydrogels that have this strength. It becomes slightly stronger if you complex it with the methyl viologen because of charge-charge repulsion of the gas molecules. So then the question comes, well, this high compression strength, is this really due to this cross-linker, or is it just because we use polyisopropenyl oxazoline that gives us a strong hydrogel? So we did some reference experiments again. So here we cross-linked the same Pipox with this diacid azelaic acid, and we cross-linked it with the diacid benzene, which is actually the reactive subunit of the pillararene that we use for the pillararene hydrogels. And if you make these hydrogels and we compare them in compression, we can clearly see that the pillararene hydrogel is much stronger than the 2 reference hydrogels, indicating that the high strength really comes for the pillararenes. And what we believe is that if we compress these hydrogels, these bulky pillararenes, they start to repel each other, they occupy a large amount of space, so you're actually also compressing and bringing these pillararenes very close to each other, giving higher strength and toughness to these materials. Well, because they're host gas supramolecular hydrogels, they can still encapsulate gas molecules. We did a quick screening if we can use this for water purification. So you see some different dye molecules that we tested to see if they are entrapped within these hydrogels by host gas complexation. And you can see here that, well, some of them, the methylene blue, the methyl red, they're quite efficiently encapsulated in these hydrogels, shown also over here. So you have a solution of methyl red, you add a small piece of hydrogel, and all the methyl red, the color, goes into the hydrogel for water purification. Same for the methylene blue. And here we showed that you can do this a couple of times. Intermediate, we have washed the hydrogel with DMF to take out the gas. We're looking at methods to do that more environmentally friendly, for example, by heating of the hydrogel pieces. Okay, that then brings me to the final part where I will still talk about the polyisopropanol oxazoline, but a different way of cross-linking. So not cross-linking with the pillarine, but cross-linking based on metal coordination. So as said, we have a polyisopropanol reactive platform, very easy to modify with all kinds of molecules having an acid group. So we bought this terpyridine, which has an acid functionality. You mix the two together, you heat it up, and you get a functional terpyridine functional isopropanol oxazoline, which now, upon metal coordination, can be used to form supramolecular hydrogels that are now held together by this non-covalent supramolecular bond between the terpyridine and transition metal ions. And this is a reversible bond, which then gives possibilities for self-healing behavior and easy reprocessing and remolding of these polymers. So this is the polymer again with the terpyridine in the side chain. This is an experiment where we show the metal complexation by titration with iron 2 ions. And you can see that up to half equivalent, we get full complexation. So we get a 2-to-1 complex, which you need for the cross-linking. We can make hydrogels with different transition metal ions. And by rheology, we can show that all of these transition metal ions induce the formation of, indeed, hydrogel materials. Well, that they are self-healing is shown over here. So this is with the complex with iron. You can see at a low strain shear force, we have a high storage modulus and a low loss modulus, indicating we have solid gel materials. If we then go to high strain conditions, 500%, we see a crossover that the loss modulus is now higher than the storage modulus, so we have liquid behavior. And as soon as you go back to the low strain, we immediately see solidification of these materials. So that indicates self-healing behavior of the materials, as also macroscopically shown here by merging the two pieces that then form and reform the bonds. Well, that is a very weak hydrogel because it's only held together by the supramolecular interactions. And to make a strong hydrogel, we actually made here a dual cross-linked hydrogel. So it's still a single network hydrogel, but we introduced two different types of cross-links. And the first cross-link that we want to introduce is based on the terpyridine metal complexation. And the second cross-link is a covalent cross-link with a diacid. So we first make the terpyridine functional polymer. We cross-link it with the diacid to make here the covalent hydrogel that we then subsequently swell in presence of a transition metal ion to make the dual cross-linked hydrogel, having both covalent cross-links and supramolecular cross-links. And here you can see the colors of these hydrogels. You see the swelling of these hydrogels, but it's probably most interesting to go through the mechanical properties, again, under compression, where we can see that the hydrogels without the terpyridine, they're relatively weak hydrogels. The ones with terpyridine in water, so here the dotted line, this actually already gives an improved in mechanical properties because of hydrophobic stacking of the terpyridines. But then with the transition metal ions, we get even stronger hydrogels, and in this case, it's really the zinc that gives you a very strong and tough hydrogel. And the reason that zinc gives a strong hydrogel here is that we used an excess of transition metal ion, and for zinc, we have a preference for the bis complex formation. And if you add more zinc, we still have the bis complex. For the other transition metal ions, if you make the bis complex and you add excess of metal, it actually opens up to make two mono complexes. So then you lose your cross-linking. So in this case, zinc was the most interesting transition metal ion. Then you see in compression, we have a strong dual cross-linked single network hydrogel. We see upon relief of the stress that we have some hysteresis, so we have some energy dissipation, and especially in tensile, this is very clear. So we have here the tensile test of the zinc complex dual cross-linked hydrogel, where we see a very strong energy dissipation, very high area under the curve, and this is resulting from the fact that if you pull on these materials, you first break your supramolecular bonds, your metal complex, that are you breaking, while you retain the integrity of the hydrogel through the covalent crosslinks. And with that, I come to the summary of what I wanted to show you today. So I showed you our work on supramolecular polymer materials to make sensors with memory function, both temperature, memory, whether it's heated or not, also the time memory function. I showed you how to make temperature-induced hydrogel swelling and actuators, and how to combine polyisopropanol oxazolin with supramolecular units to make strong and tough hydrogel, and as well to make energy-dissipating hydrogels. Well, a small disclaimer, that I'm also a founder of a spin-off company, Avroxa, which is aiming to commercialize polyoxazolin, so I'm here today in my role as professor from the university, but as a disclaimer, I'm also involved in the commercialization of these polymers. And then the final slide is to acknowledge the people that actually did the work that I've been showing today. So you see a recent group picture that we made earlier this year. You see here on the left, the people that are in the group, the people in red that are mentioned, are the ones that did the work that I've been showing today. And I also have to acknowledge the collaboration with Patrice Wazel for the host gas complexes, and with Adriana and Victor, who are now both faculty members in Bucharest in Romania. And if there's any questions remaining, I will be happy, of course, to answer them. Thank you.
Thank you so much for a fascinating lecture. We can take probably 2 or 3 questions. Yeah, Anil? 1 minute. Anil?
Yeah, very interesting talk. I have a question on that time function, the time memory. So if you randomize your sequence, the state which you reach, does it depend on from where you're coming, or that's a thermodynamic state now? Because once you're reading as a memory, you'll only know the final state. Yeah. But how do we read the history from there, what has happened in that sequence?
That's a good question. So the time memory is not in thermodynamic state. So this is a kinetic state of the sample at a certain time point. So the way we envision this to work is that you have the hydrogel in an aqueous environment, and it's there at a certain temperature, and the moment you want to read it out, you have to take the gel out of the solution and re-swell it in fresh water. And then you can read out the time that it was heated in the original flask.
Okay, so there's no timestamp, because that you can anyway manually be measuring it in case if you know the sequence. But that's okay, we'll discuss that.
Yeah, indeed. So if you exactly know the time, of course, for these experiments, you can just record the time. But if you have a variable time, then by looking at the state of the gel, you can determine the time.
Yeah, it's a great talk. I have some question about the third part of your talk, particularly the working principle by which your temperature-induced swelling happens. I'm really surprised that at 38 degrees centigrade, the TTF and this charged acceptor complex breaks, because it had the option of still remaining in water by aggregating the NIPAM chains, like it happens in double hydrophilic polymers, where one of them is like NIPAM. So I'm really surprised why the complex has to break at 38 degrees centigrade and go inside the hydrogel.
Yeah, that's a very interesting question, and that's a question that we've been trying to address in recent years, and it turns out that it depends a lot on the properties of the host that we're using. So the host that we use has 4 cationic charges, and because of that, it's extremely hydrophilic.
Yeah.
And because of the high hydrophilicity, upon collapse of the polymer, the host partitions from the phase with very little water and mostly polymer, it partitions to the water phase. So if you would do the same with a cyclodextrin, which is not charged, the cyclodextrin will stay in the collapsed phase.
Okay, thank you. Yeah. So we have 3 more very quick questions. I'll request those because to be very brief.
Okay. I have the question regarding the hysteresis effect of LCST. So you have measured, I think, by changing the hydrophobic, hydrophilic balance, and you are getting the hysteresis. Have you played with concentration? Because LCST is always a U type of curve in the cloud points. So if you change the concentration, do the hysteresis vary?
We have looked a little bit at the concentration effect, and the hysteresis remains. So the key to get hysteresis is that in the solubilized state, you need to have hydrophobic groups that are hidden inside the hydrophilic polymer when it's hydrated. And then as soon as the polymer collapses, it gets dehydrated and you expose these hydrophobic groups. And the exposure of hydrophobic groups makes it much more difficult to redissolve the polymer. Yeah, that's also possible. So because of this thermodynamic principle of inducing hysteresis, it also works at different concentrations. Yeah.
Richard, quick question. That regarding the hysteresis that which you have shown that, thermoresponsive polymer going from one state to other state like a sigma diol is okay. But then we have a secondary parameter where you have a guest-host interactions. So in that case, if your sweeping time scale, if you change, probably you would have had a step-wise sigma diol plot rather than a single step, correct?
I'm not sure if I got the question.
Would you have a single step sigma diol plot from going from one state to other state in the case of thermoresponsive systems?
Yeah.
Now we have another component, you have a guest host chemistry.
Yeah.
Then in that case, the slowdown should happen, you have a stepwise process rather than a single step process. That's what we want to anticipate.
Yeah, so you have indeed the two phenomenon interplaying at the same time. So you have the collapse of the polymer and the host gas complexation. And to induce the hysteresis and get the collapse of the complex polymer, we need to use strong host gas interactions with association constant of 10 to the 5 or higher, so that by increasing temperatures, you do not first lose your complex. Because if you would lose your complex, your polymer gets more hydrophobic and collapses. But we have confirmed with reference polymers, so if you use a polydimethyl acrylamide and we heat it to 80 degrees, it remains complexed. Yeah. It doesn't decomplex. Only with the NIPEM at 30, it decomplexes, indicating that it's related to the LCST phase transition.
So you can see the interest in your talk by the audience. We'll take one last question, and then the others you can take up in the tea time.
In the slide you mentioned about the removal of pollutants by using these hydrogels. Is it because of this mesh size difference or the affinity of the pollutant to the hydrogel interaction?
Yeah, so the interaction that I've shown between the dyes and the hydrogel, it's related to the formation of the host gas complex with the pillararene. So if we use the hydrogel without pillararene, with another regular crosslinker, we don't see this absorption of the dye in the hydrogel. So it's really the specific interaction.
No, that's it. I have to cut it somewhere.
After.
Thank you so much. Thank you so much. Let's give him a big hand. So now we have the next lecture. It's a Professor Kishore Memorial Award lecture, about which Professor Ramakrishnan had mentioned in the morning, and this will be delivered by Dr. Samir Chikali. He is a senior principal scientific officer and professor at the Polymer Science and Engineering Division, CSIR National Chemical Laboratories. Samir. So your talk is 30 minutes, so 25 minutes, and then we'll take question answers.
Slide changer. A very good afternoon. Am I audible? Okay. Thank you, Professor Mishra, for the kind introduction. At the outset, I would also like to thank the Society of Polymer Science India for the Kishore Memorial Award. I will try to make up for the 5-minute time we have lost, and will try to complete in about 20 minutes. So today what I'm going to do here is try to give glimpses of 2 topics that we are pursuing in our research group, not to try to combine everything and try to speak about everything in about 20 minutes. So today I will be talking about insertion polymerization of ethylene, quo vadis. Quo vadis is a Latin term. It was, if you try to translate it in English, it says, where are we going? So polyethylene, as you have heard since morning, is a 70-year-old polymer. The question now is, where are we going? I mean, is it still interesting material, or is it bringing new features to the same old material? So I will try to bring two features to this old material. Before I do that, I would briefly like to introduce the research that I pursue at NCL. Research in my group integrates various elements of ligand designing and then designing metal complexes, which we use for various applications, for example, to activate small molecules or to make larger molecules like macromolecules and polymers. We also use this knowledge to make renewable monomers, renewable and degradable polymers. Today I'm not going to talk much about that, but I will be talking more about this. We just do not stop at making these ligands and complexes, but we try to use them to solve scientific puzzles of fundamental importance. And once we address that, then we try to use this knowledge and try to solve some real world problems in collaboration with different industries. So I will be talking today about insertion polymerization. Now this polymerization is taught in master classes and maybe in some bachelor classes. So if you talk about ethylene polymerization, it's not that the first time Professor Ziegler and Nata, they discovered, but before that there was also a process which is called high pressure process, which was a radical polymerization. And if you look at the pressures that were required and temperatures, huge pressure is required to really activate ethylene and to get polyethylene. What Ziegler and Nata, they could do is they made a catalyst, okay, which reduced this energy requirements, so pressure and temperature. And if you use these Ziegler type catalysts, one can run the ethylene polymerization at 10 bar and 70 degree. Okay? So that's where the knowledge of organometallic chemistry and catalysts is very important to address some of the fundamental challenges that were faced in those days in 1950s and 60s. So this field has traveled a long distance. Out of 380 million tons of polymers that we produce today, roughly 50 to 60% are polyolefins. So we produce about 200 million tons of polyolefins every year in these huge plants. I think if you talk about India, we produce about 6 million polyethylene and about 4 million polypropylene. So this is well said chemistry, but if you try to make a very small change, instead of taking this ethylene, if you try to bring a functional group here, so if you take ethylene or propylene, you have a propylene, you have CH3 here, but if you change this CH3 with, let's say, ester or acid like acrylic acid, the same 70-year-old chemistry doesn't work. Okay? So if you take acrylic acid and use Ziegler catalyst, you will not get any polymer. So why is this? I will try to address in next few minutes. But before I do that, why people are interested in making functional polyethylene? Okay? The idea here is there are a lot of other applications where currently polyethylene cannot be used. For example, you cannot use polyethylene for paints, you cannot use it for coating because there is no functionality, there is no adhesiveness. So these properties are required and polyethylene doesn't have. So people are looking at, okay, can you functionalize polyethylene? There are two ways. One, you can do first make polyethylene and then functionalize, called post-functionalization. The other one is when you are making polyethylene, can you functionalize it? Okay? So to do that, if you have to take ethylene and then a functional olefin like acrylic acid or methyl acrylate and polymerize, and then maybe some of these properties can be also delivered by polyethylene or functional polyethylene. Now, why it doesn't work? If you take a functional olefin like acrylic acid and ethylene and try to do a copolymerization, forget about homopolymerization with functional olefin, but even if you try to do copolymerization, it doesn't work for mainly three reasons. One is if you take ethylene and a metal catalyst and let's say you have acrylic acid, if you try to polymerize, ethylene is a very small molecule, it's electron rich. So in the coordination competition to the metal catalyst, ethylene wins. So ethylene coordinates to the metal much faster compared to this one, and then it inserts. So this is one challenge where if you want to make a functional polyethylene, Okay, you cannot beat the electron density and small size of ethylene. So the coordination of ethylene is going to be always faster, and then you will end up in polyethylene. If you try to play around this, you can increase ethylene pressure and maybe reduce functional olefin. Then you end up into a second problem, where in the functional group, if you have a ester or if you have acrylic acid, the oxygen has two lone pairs. So those lone pairs can coordinate to the metal and block your polymerization site. So again, there will not be any polymer. So the third one, if you win over this, you can try to do that by changing your catalyst. You have to play around with the electronics and sterics of the catalyst. If you win on this, then you can force the polymerization to go into this direction. The last hurdle is, even if your acrylic acid, let's say, inserts, you are managing to insert, after insertion it can form a chelate. And if this chelate is stable enough, again there will be no polymerization. So this is the reason why ethylene functional olefin copolymerization in situ doesn't work. Now there are people starting from Professor Bruckart in 1995 who have developed different catalysts. Okay? So Bruckart catalyst, here the metal is palladium in his case, and it can tolerate a lot of functional groups. But the limitation there is one can introduce only about 3 to 4% of methyl acrylate, and that too it is at the chain ends. Okay? The most successful system among them is this Drent system or phosphine sulfonate system. This has been able to tolerate a lot of functional groups. Of course, there are limitations with each functional group, how much you can incorporate and what molecular weight you can achieve. But this system is able to tolerate. So when we started our research at NCL, we were wondering if the aim is to increase the functionality in polyethylene. Should we only limit to these kind of monomers where per insertion you will get only one functional group in your polyethylene chain? Or should we look at olefins which have two functional groups? So if I can introduce or insert this olefin into my polyethylene chain, per insertion I will have two functional groups. That means I'm increasing the hydrophilicity of this polyethylene that I'm preparing. So with this aim, we started looking at what catalysts are available, where we can tailor. So there are two critical things that when we look at designing the catalyst. So one is that this donor atom, because if I want to insert this donor atom should be very labile. As soon as ethylene comes or functional olefin comes, this donor atom has to leave and create a vacant site for ethylene. Okay? The other one is looking at this oxygen. It plays an important role on a palladium d orbitals by taking electron density and stabilizing the pi complex with palladium. So with this aim, we looked at two target monomers. The first one is very interesting monomer. If you buy a Feby stick from the market, in that the molecule is this one. This is called ethyl cyanoacrylate. It's a glue. We use it in our daily life. We said, can we incorporate this glue into our polymer chain or in our polyethylene chain? Before I do that, I will talk a little bit about making this catalyst which we are trying in functional olefin polymerization. So as I told, phosphine sulfonate has been the most successful catalyst in last 15, 20 years. We were trying to tailor this catalyst so that we can use difunctional olefins in copolymerization. What we have done is, in our initial efforts, we had two-step process, but we have now cut it down to single-step process where we can get this complex. Now, whether this complex has been formed or not, there are different techniques. One can use NMR, IR, and so on. The final proof comes from single crystal X-ray diffraction, where you can actually look at the molecular structure of the complex. What you can see in this case is you have a phosphorus, palladium, and oxygen, and this angle and that angle should be cis. So if this angle is not cis, so in olefin polymerization, one has to understand that if you have a metal complex in the center and you have a metal R bond, then the incoming ethylene has to come and insert between this metal R bond. If this angle, the carbon, the metal, and incoming ethylene, this angle is cis, then only insertion happens. If this angle is trans, let's say ethylene is coming from down and the R group is sitting here, it doesn't insert because it has to insert. So we have to look at this angle, which if it is cis, we will be able to get an active metal complex, which will be able to polymerize ethylene or functional olefin. If this angle is not cis, it may not be active in polymerization. So therefore, it is very important to look at crystal structure and find out if the angle is cis or trans. So we looked at this, and you can see in this case, the angle is about 91. So it is a cis angle. So in organometallic chemistry, it is already defined what is a cis angle versus what is a trans angle. If the angle is less than 105 degree, it is called cis angle. If the angle is more than that, it is called trans angle. And here we have about 91. So we know the crystal structure. What will happen when I use this in polymerization, I don't need any co-catalyst. It's a self-activated. As soon as I add ethylene, this acetonitrile will go away, ethylene will come, coordinate, and will insert between palladium and this carbon, and the chain can grow. Same thing if I use acrylic acid should come, coordinate here, and then insert. So we use this catalyst, and we looked at copolymerization of this ethyl cyanoacrylate or crazy glue. So we had ethylene, then we had ethyl cyanoacrylate. We take this catalyst, the amounts and moles have been mentioned at the bottom. So when we do polymerization, we get a copolymer. This is the reactor, how we do our copolymerization. You can see in this table that we have varied ethylene pressure, we have varied the concentration of this, and then based on that you will have yield, different yield, and then incorporation, how much of this is incorporated in your final polymer chain, and what is the molecular weight and PDI. So what you can get from this table at higher pressure, you can see that we have better yield, but the incorporation is only 0.3%. Whereas if I reduce ethylene pressure and increase concentration of ethyl cyanoacrylate, we get increased incorporation. Of course, it comes with a price of reduced molecular weight. Okay? So we could get about 6.5% incorporation. That means double the amount of functional groups. So if it is 6% incorporation, the functionality is about 12% now. Okay? So this was our first attempt to look at insertion copolymerization of functional olefins with ethylene. We have proved this incorporation by different methods. Here is high temperature proton NMR. So one more thing, so polyethylene as such is not soluble in at room temperature in any solvent. So whatever characterization we have to do it at high temperature. So this is a high temperature NMR at 130. So what we can see, these two signals, A, B, and C, these are the characteristic signals where we can look at the integration of this, and based on that integration, I can calculate how much is the incorporation. So this is how we have incorporated ethyl cyanoacrylate and calculated the incorporation. We have also looked at and compared with homopolymers, copolymers, and physical blend. So what we are trying to show in this one is if you have only homopolymer of ethyl cyanoacrylate, you will not have these three signals. Whereas if you have a copolymer where ethyl cyanoacrylate is inserted in the main chain, then you can have these three signals. We have also done a 2D NMR. We have looked at proton-proton correlation, wherein you can see these A protons show a cross peak to B protons. That means they are in the same chain. That means ethyl cyanoacrylate is incorporated in the main chain. We have went further looking at insertion products. So what we have done so far, I showed you, we can take ethylene, we can take ethyl cyanoacrylate, use our catalyst, and we get a copolymer. Now what I'm trying to do here is I'm just taking the catalyst and then I'm looking at insertion. I'm not adding ethylene here. I want to see if this monomer can be inserted. Okay? So there are different possibilities. First is 1,2 insertion. That means this is carbon number 1, this is carbon number 2. It can insert in both ways. So I'm looking at whether it is going via 1,2 insertion or 2,1 insertion. So for this, what we could see is it is showing both 1,2 insertion and 2,1 insertion. Whereas for this, the second monomer with the acrylic acid group, we could not see this 1,2 insertion, but we could see only 2,1 insertion. In the next step, what we have tried to do is we isolated this. So we tried to look at the isolation of this, and we also got, fortunately, a crystal structure wherein you can see that the double bond, which was this double bond here, has been opened.
the methyl group which was on the palladium has been transferred to this carbon and it had formed a palladium carbon bond. That means it's a 1,2 insertion, and that's what the product we have. And you can see in the crystal structure palladium with this carbon C10, and the methyl which was there on the palladium has moved to the C9 carbon. And you can see that this oxygen is actually forming a sort of electronic interaction, so it's coordinating. Now if this has to act as a catalyst, this coordination has to break, ethylene has to come, and then it has to insert. So this coordination should be very labile. If it is very strong, this will not be able to polymerize ethylene. So this is another test to say that the functional olefin inserts and it is able to polymerize ethylene. So we took this complex and then pressurized with ethylene. So we have taken this complex 8, which has already an inserted functional olefin. Then we pressurize with ethylene. What you can see is you get a polymer, and when we quench, you get P3. So wherein the chain, one chain end is your monomer that you had started. Now if I want to compare this, for that purpose we made model compounds. So we synthesized by a different method the same compound M3 and this P3. So if you look at the NMR, they exactly match, which basically shows that this inserted product is able to open and insert ethylene to give us this polymer. Okay. So with all these insights, mechanistic insights, we thought now we are ready to explore the scope of this, and we looked at different 1,1 di-substituted di-functional olefins. In this table we have presented about four of them. As you can see, there are 2 parameters that we have varied. One is ethylene pressure, the other one is the concentration of the monomer. So depending on what groups, functional groups we have, there is different incorporation. We get maximum about 6% incorporation. We then moved slowly to allylic monomers, wherein now the double bond is 1 carbon away from the 2 functional groups. So in this case, I get more incorporation. We get about 12% incorporation. That means now the functional group density is about 24% of that. There are different methods to say that whether now the final polymer is hydrophilic or hydrophobic. We have done some of these tests. One of them is water contact angle, simple water contact angle. So we can make take this polymer and spread it on a surface and then look at water contact angle. If you take simple polyethylene prepared by using the same catalyst, we get about 112. Now as our incorporations increase, this water contact angle drops, and for the highest incorporation we have about 76-degree water contact angle. That basically tells me that this is highly hydrophobic. Now I have introduced functional groups, so this becomes much more hydrophilic. So this is one part that I am looking at. We have expanded this, but we have still not published. We have used this to compatibilize 2 incompatible polymers and see whether we can use them as a compatibilizer. I will slowly change gears to the second topic. So this was about functional polyolefins, so I can still use ethylene even after 70 years to make a different type of polymer which can serve different application. The second one is about a polymer called ultra-high molecular weight polyethylene. So some of you might have heard, this is not new. Again, ultra-high is being commercially produced for at least 40 years. There are different definitions, but if you go by ASTM, polyethylene which has molecular weight more than 2.5 million grams per mole is termed as ultra-high molecular weight polyethylene. There are different definitions of that. So if you look at the commercial one, there is a molecular weight which is very high, because of which these chains fold, not just fold, but they entangle. That means they form knots. Now processing of this polymer is difficult, and there is already a process, gel spinning process, which was developed by DSM in 1970s. So what you have to do is you have to take this polymer, 5% of that, and dissolve it in 95% of solvent at about 200 degree, and then you get a gel, and from that gel you can spin out fibers. Okay? This is standard process, well established, commercialized, and everybody uses. Okay? But dissolving this polymer and then processing with 95% solvent is something which people are trying to go away from that. So the idea here is, can we make the same polymer but avoid these entanglements so that it can be melt processed rather than making a gel and then trying to spin out a fiber. So the change what is going to happen is instead of ultra high, which is entangled one, can we make disentangled ultra high molecular weight polyethylene? So it is same polyethylene, but only thing is we are trying to avoid these entanglements. Instead of that, it is now much more crystalline. So I am not allowing my chains to entangle with each other. How we can do that? There are different ways I will tell in next few slides. So when we were trying to look at which are the catalysts that the industry uses, what are the catalysts that the literature shows us, that industry uses mostly heterogeneous catalysts, but that gives entangled ultra high, okay? Whereas these are the two catalysts that have come up in last 10 years, that these are homogeneous catalysts, that those are able to give disentangled ultra high. Now they have a lot of applications where it goes. I will not talk much about that, but you can see that heterogeneous catalyst giving ultra high, which is entangled, whereas homogeneous catalyst giving disentangled ultra high. We were trying to understand what is the difference, why one is giving entangled, whereas the other one is able to give disentangled. There are two major differences. One is if you look at typical Ziegler catalyst, which is used for this, the oxidation state is not very well controlled. So you can have +1, +2, +3, +4, all different types of oxidation state, and this can give to different chain lengths. And now these can entangle, that's one part. The other part is it's a multi-site catalyst, whereas these are mostly single-site catalysts. That means one metal center is giving you one single chain, and if you can avoid chains coming and entangling, you can get disentangled. So when we were trying to look at, we said, can we take the heterogeneous catalyst and do a controlled reduction? So I'm taking titanium +4. Now I'm trying to do a controlled reduction, and in Ziegler's chemistry, it is known that titanium +3 is the active oxidation state which gives you polyethylene. So we were trying to control whether we can reduce titanium 4 to titanium 3 without allowing it to go to 2, 1, and 0. Okay? So we did different experiments. Now these experiments are not easy also, because if you take titanium, Ziegler catalyst, these are highly moisture and air sensitive, so you cannot do it. Now if I want to look at oxidation state and do a controlled reduction, how am I going to do this? So fortunately in NCL we have very colleagues who are very interested looking at this. We collaborated with Vinod. I think Vinod is not here. So what we did is we developed a vacuum suitcase, okay, which can go into the glow box. So we developed with local vendors a suitcase which I can evacuate, I can take it in the glow box. Then I do my controlled reduction in the glow box, and then I take that catalyst, load into the suitcase, bring it to XPS and look at the oxidation state. So this is how we try to do controlled reduction, and we found that if I use aluminum to titanium ratio of about 600, I get titanium +3 as the only oxidation state. So 99% titanium +3. So we freezed on this ratio, and then we use this ratio in our polymerization. Okay? So what we could do is use that ratio and then do a polymerization at about 40 degree. When we do this, what we can get is a polyethylene with a melting point of about 146 degrees centigrade. Okay? This one way tells you that it's highly crystalline, okay, but doesn't tell you whether it's entangled or disentangled. Okay? So to look at entangled and disentangled, we did a lot of DSC experiment, and Professor Sanjay Rastogi, who has been a pioneer in this area, so he has developed a DSC method to distinguish between an entangled and disentangled polyethylene. So we used the DSC method. What it does is I have shown here. So you take polyethylene, heat to about 160, hold it at different time. Okay. Now these molten chains can then start entangling again, because entangled state is the most stable state. So when you melt polyethylene and hold at 160, you have enough movement of the chains and it can entangle. So if I do this at different time sets, then I can find out whether it is entangled, disentangled, or it's a mixture. So what you see in this plot is we have done this at 5 minutes, 15 minutes, 30 minutes, and 60 minutes. So you can see this green curve, which is for 5 minutes. This higher melting at 140, that is more. If I keep this for longer time, for 15 minutes, the disentangled state slowly starts going to entangled state. So you can you can see that the disentangled state is going to entangled state. So this indirectly proves that the polymer I made was initially disentangled, and if I am keeping it for long enough, it is going to entangle state. We have done also rheology, but Professor Mishra shows me 5 minutes, so I probably have to stop without talking much about rheology part. So this is another way to look at whether it is entangled or disentangled. We can compare with the entangled commercially available sample and with our sample and try to prove that it is disentangled material. We have also compared the activity, molecular weight and polydispersity with literature catalysts. And as you can see here, we are much better than the heterogeneous Ziegler catalyst, but if you look at the homogeneous system, we get much higher molecular weight, dispersity is also okay, but the activity for the homogeneous system is much higher than our catalyst. We have also scaled up this process. We have reached to about 3 liters, so in one go I can produce about 400 grams of this polymer. We are trying to scale it up further. We are also looking at different applications, but today I will not talk about those applications. With this, I would like to thank my students who did this work for ultra-high molecular weight polyethylene and functional polyolefins. Some of them are now postdocs elsewhere. I would also like to thank funding agencies and all the companies who sponsor my work. Thank you.
Thank you so much for an interesting talk.
If there are any questions, I will be happy to answer.
We can have a couple of questions. One question I had in the first, when you make a copolymer, have you seen the sequence of the of ethylene and functionalized group, or is it?
So
I mean, is it a random or is it?
It's a random. There is no sequence because it's only about 6% incorporation in the whole chain. So after how many repeat units?
Just saying it's only 6% does not make it random. So
okay. So it does not make it random. What we could say is it is in chain, it is not at the chain end. So if it is at chain end, we can distinguish. But if it is in chain.
So basically the answer you really don't know.
Really don't know whether it is sequential.
Yeah. Yes.
Thank you very much for this nice talk. But just for curiosity, how you determine the molecular weight, 2 millions, 2.5 millions, and also the polydispersity?
For the ultra high?
No, how you determine that? How? What method you are using in order to determine the molecular weight, because it's very high, and
for the ultra high molecular weight polyethylene. Okay. So we have done it by both methods. We have done viscosity methods, and whatever data I showed is by using STGPC, high temperature GPC.
GPC, the CSIR, is breaking down the high molecular weight. It's very well known that.
Yeah, it might happen. So it is not like all the high molecular weight is going, but whatever we could detect is what we have shown. We have done also viscosity, where we have looked at the viscosity, but you don't get polydispersity by viscosity method. So the only way to get that one is to do GPC. So
maybe by rheology?
Yeah, rheology also we have done, but I did not talk about that. So rheology also we have done.
Samir, very nice talk. I was curious about the Brookhart catalyst that you used in the first part of your talk. Is there any chain walking at all, or is it completely linear?
So the Brookhart catalyst does a lot of chain walking, and that's why the functional groups are introduced only at the chain ends.
So that's something you didn't mention. So I was not clear whether you get a linear or a branch system.
Yeah, no, it does a lot of chain walking, and it's a highly branched system.
Yeah, Shamir, it's very nice talk and very nice work. I see that in the paper of SPSI-MACRO-2022, I see the molecular is very low.
For the functional polyolefin.
Yeah. So this is the homopolymer or the copolymer?
It's a copolymer.
But molecular is very low. Why? Because your the insertion mechanism is restricted or what?
Yeah, because if I increase the concentration, okay, if I want to increase molecular weight, I can, let's say, increase ethylene pressure, I will get much higher. Okay, same catalyst if I use without functional olefin, I can get 20,000, 1 lakh and all that. But if I want to introduce functional group, so I cannot use high ethylene pressure because the incorporation will reduce. So if I want to have incorporation, I have to reduce ethylene pressure, and increase functional group, the functional olefin concentration. So if I increase functional olefin concentration, the functional group can coordinate back to my catalyst. So that reduces the activity itself.
So the two functional groups in the same way, this is a dikinal, and there will be a lot of steric hindrance.
Steric hindrance for the insertion. Yes, it is, but if you see, I have shown in a single crystal that it inserts, and if I take that one, it still opens and there is a polymerization. There is steric hindrance, that's why the activity, molecular weight is not same as if you use only polyethylene.
I think we can continue the discussion later because time is running out. You didn't finish 5 minutes early, so.
Sorry about that.
As you promised, but that's all right. And I'd like to talk to you about this disentanglement because I don't believe in disentangled long chains it will happen. Anyway, we'll discuss that later. Okay. The next lecture is a plenary lecture. Thank you so much and let's give him a big hand. So the next lecture is by Dr. Valery Kapelyushko. He's a Solvay Fellow, Head of the Advanced Research and Sustainable Technologies
It's better to stay here. No, no, I am okay. Mr. Chairman,
Hello. Yeah, we will start the sessions. Everybody please take the chair. So for this session, the chair is Professor N.N. Maldar. He is a professor of chemistry and I request him to chair the session and do the deliberations.
Good afternoon, everyone. Now it's indeed my pleasure, privilege, and I'm honored to be associated with the MACRO-22 and the special event to be held on 4th of November. It's like a homecoming for me. And today we have two talks. The first talk will be by the Professor Nikos Hadjikistodis, and second talk will be online after that first talk is over. Now let me briefly say, the Professor Nikos is presently with the KAUST, Saudi Arabia. Initially he was with the University of Athens, Greece. And I would say in the synthetic polymer chemistry, he is a true craftsman. He has prepared a lot of polymers, aesthetically good-looking macromolecules with architecture. And he is one of the few living frontier polymer chemists and practitioners of the anionic polymerization, which is the gold method for the synthesis of the precision polymers. Now, Professor Nikos, he did wonders with his creative mind and synthetic capability and contributed immensely to the progress of the synthetic polymer chemistry. I would say, if I'm not wrong, he has got the highest number of publications in the macromolecules by any polymer synthetic scientist. He is 80 plus, and if you look at him, I will say that still he has got high enthusiastic and precision and profiling publisher here. Now, lastly, what I will say that Professor Nikos, he is a good friend of the Indian polymer community. He said just now, I love India, that's why I have taken a lot of trouble. He would travel overnight and he reached Pune in time. And I will say that he has contributed indirectly to the growth of polymer science in India. So, Professor Nikos, please.
Professor Ghosh, thank you very much. You are right. I love India. I love the colors. You know, it's the country of colors. And I have many friends here. So that's why I was traveling the whole night. I arrived at 10 o'clock at the Mumbai airport after the car 3 or 4 hours, and I came directly here. What does it mean? It means that I love India. So before I start my talk, don't forget to take out 5 minutes because you took 5 minutes to introduce me. So before I start my talk, I would like to thank the organizers, and in particular Professor Asha, Professor Samir, Professor J. Kanan, and of course the Patriarch, Professor Ramakrishnan. Thank you very much for this kind invitation. I don't forget my friend Professor Sivaram, of course. So what I am going to talk today is about another way to make different macromolecular architectures. I don't like the complicated system. I like the complex macromolecular architectures, but these complex macromolecular architectures should be model. It means that all the molecules must have the same molecular weight. Nature only is the perfect chemist that is doing polymers with 20 amino acids, is putting a different position, and all the molecules are exactly the same. So compositional homogeneity very high, structural and molecular weight. So there are complex but not complicated. So I will highlight today another method to make complex macromolecular architectures. And this method is through non-static covalent bonding. This is through either hydrogen bonding, dynamic covalent bonding. You know only vitrimers, but you can make different macromolecular architecture based on dynamic covalent bonding. Think a star polymer. The star polymer has relaxation of the arms, but think about that the arms can be changed between them. This is the dynamic covalent bond. So you give more problems to the physicist, and I love that. That's why I'm making all this complex macromolecular architecture. I like to give challenges and problems to the physicists. It's completely a new physics if you have these molecules. So all these years, what I was doing model macromolecular architecture. I was doing macromolecular engineering. There are a few of these structures here. The different colors are different molecular weight or different chemistry. But the polydispersity, the compositional dispersity, and the structure is very low. So these polymers were gold for polymer physicists, and they solve many problems. I can say they advanced polymer physics. So here, for example, you can have the different color, all the polymers you can imagine. I put a few of them, styrene, polybutadiene, but you can have PVDF, polyoxazolines, you have polylactides, etc. And I am using all the methods, only living methods. And lately, I am using the C1, C3, and C5 we discovered at cows. So here you have the static covalent bond. All these are static covalent bond. If I talk about static covalent bond, is the junction point. The chain is covalent, still covalent, but the junction point is covalent here. So here you have model polymers and macromolecular engineering. Anionic polymerization is one of the methods that is leading to these model polymers. And why you need model polymers? You need in order to have accurate structure-property relationship. It has a very big impact in polymer science, in polymer physics, and in polymer industry. So why? Because the heart of the properties
is situated, lies at molecular level. If you are able to change the molecular level, to control the molecular level, you are able to control the macroscopic properties of the materials. That's why I'm doing all that. So, importance of model polymers in polymer science and polymer industry. Testing existing theoretical concepts. I will give you not very details. I will give you two only molecules that how they help the polymer physics. And after developing new theoretical concepts to explain experimental results, understanding improving the properties of industrial polymers, polyethylene, or thermoplastic elastomer. So I have a collaboration with all the physicists. Name a physicist, and I have collaboration. So the dark blue is the collaboration I have now. And the light blue are the collaboration in the past. And here are the companies. And here, for example, we have, I will give you two examples. This is, we call inverse star block copolymer. Inverse star block copolymer, it means that each arm is a block copolymer, polystyrene and polyisoprene. Two arms are coming to the junction point with the blue chain, the polystyrene. The other two arms are coming with the red. And this is 50%. And this is the only morphology until now that this is double diamond morphology. This is two interpenetrating, two network, functionality 4, the interpenetrating but not touching each other. So Ned Thomas told me, Nikos, we did the calculation. If you can prepare that, we are going to have the only morphology of neat polymers. You can have by mixtures. Okay, here for example, here there is in rheology, in molecular rheology, we call a hierarchy of motions. There are 3D dendritic polymer. There are 3 generations, the external, the second one, and the internal. So here there are 3 relaxations, 3 plateau moduli. Without this polymer, you could not solve this problem. You could not prove that the theory was was accurate. So if you make polymers by other methods and you do the rheology, the theoretician will tell you they are not good. Our theory is for perfect polymers, okay? But here they cannot say anything. Now, what we are doing now is we are using these 3 kinds of the bonding I explained to you on the first slide. The first is hydrogen bonding based polymers. For example, instead of having here the covalent bonds, you have the hydrogen bond. Here, instead of having here the covalent bond, you have the dynamic covalent bond. And here, instead of having the covalent bond, you have the stereocomplexation between the PTLA and the PLLA. So, in order to do that, you need good physicists. And I collaborate for morphology with Professor Ned Thomas, Texas A&M University, and for rheology with Dimitris. He's a compatriot, which is one of the best in molecular rheology. Now, I think that Professor Nyanyou saw this slide in the morning, and so I am not going to say anything. This is speaking about macromolecular engineering. This is a 5-volume book. It took us 5 years to do that. And you see here many of the best scientists are contributing to this book. Now, let me give you example. I cannot go to many details. I like to give you a flavor in order to convince you to work on this area. Now, let's say how we can prepare a copolymer and what is the morphology of this copolymer if instead of static covalent bond, you have the hydrogen bond. And we choose this thymine, and here is the diamine triazine, okay? Because they form 3 hydrogen bonding. So in order to do that, you can, of course, you can prepare star, you can prepare comps, you can prepare anything you like. So we have a very powerful tool called not an ionic polymerization, high vacuum techniques. It's very difficult to do. It's time consuming. You have to know glass blowing. You prepare a few milligrams or grams, but this is the penalty you have to pay if you like to have model polymers. And these polymers, and I have example not today, I don't have the time, they guided the industry. Because otherwise with this, without these model polymers, industry was blind. So among all the structure, you pick up one that is doing the job. And after you have to find a industrially feasible method. You lose a little bit of the advantages, but you have already won a lot. Now, how we make that? First of all, we use a protected initiator, the polystyrene, and after we deprotect, and we have the amino-terminated polystyrene. On the other side, we prepare the almost 1,4 polyisoprene. Of course, you know that one of the problems of anionic polymerization is to prepare 1,4 polyisoprene or polybutadiene. We can prepare 100% 1,2, but not 1,2. The reason is that we cannot find an initiator that is not polar. So maybe we have to go to organocatalysis, but this is not so easy. So after that, we make the post-polymerization reaction, and we put at the end, we fractionalize either with the DAT or with the thymine. And here is the GPC, and you can see here that the precursor before the reaction to transform that to omega hydrogen bonding groups, they are much better than after the transformation. And the reason is that instead of the hetero bonding, you have the homo bonding, because the two, they can form hydrogen bonding. So that's why you have a little bit on the high molecular weight, this small peak. Now, in order to make the copolymer, for example, you dissolve in the trichloroethane. We can do directly the NMR. As you can see here, I'm not going to go through all this. I'm going to go only on this in the polyisoprene. This is the A. This is the A of this amine hydrogen that after the complexation, after the formation of the hydrogen body should be changed. So should go downfield. So you can see here that is going, here is the two precursors, and you can go from 8.15, you go to downfield to 881. So this is a proof. And after, another proof is the following, that we prepare, of course, a few polymers. Another proof is that if these are hydrogen bonds, by giving energy, by heating, that's by increasing the temperature, is going to go upfield. And it's going until 85 degrees, 805. If you go to 90, it's the same. If you go back to 25, you see that this is the same. It's coming back from where started. Now, here is the TEM. The polyisoprene is stained with osmium tetroxide. This is the TEM, that Ned Thomas did. And here, in the case of, you have 15, 15, so should give lamella, and here is the corresponding covalent bonding die block. We have to compare. You see that this is lamella. Here also is lamella, but the problem is that the despacing, one white, one black, is much bigger than the despacing of the normal die block polymer. And the reason is, again, the HOMO association, the HOMO hydrogen bonding, is going there and is dwelling the two microdomains. Now, here, of course, is not very good, but you have some domain separation here also, because here you see is the cylindrical, but you have here cylindrical, you have warm. This is not so easy this hydrogen bonding is not as good as the covalent bonding. So here, but they are blockopolymers by hydrogen bonding, because here is the mixtures. This is the mixtures. So it's micro domain. It's not in this regularity in the case of the hydrogen bonding. Here are the TEM, the Sachs pattern of the three diblockopolymers, the normal and the other. The density is higher, but you can see clearly the peak. But the density where should be is there. So I repeat again, it's not so easy, but these are the results, okay? Now, here is the TG. Also, you can see that this is phase separation. And now, let's go to do the following. We have a diblocopolymer that has the theme here, and we have a polystyrene that has the diamino triazine. So it means that it's going to change the composition. If they form the triblock, here, if the composition of polyisoprene is higher than polystyrene, that will be cylindrical, for example. But if you do a triblock with polystyrene, the composition of styrene is increasing, so it's going to change the morphology. So it's again, I'm not going to repeat again the same story. And here you can see that you have the blockopolymer, you have the cylindrical structure. Here you can see this is the mixture. Again, this is the diblockopolymer that is diluted by the homopolymer. This is a mess. So despite the fact that they are formed, the morphology is not as good as the corresponding covalent bonding blockopolymers. Here you have styrene, you have the cylindrical, and you have also the swelling lamella. Now, let's go a little bit to well-defined vitrimers. And we are using the acetaldehyde and the triamine in order to do the dynamic covalent bond. And here is the vitrimers, but here we are working on making the three-arm star, having at the junction point not covalent bond, but having the dynamic covalent bond. And here you see that for those that maybe they have not read about that, we have the thermosets, permanent network, and we have the thermoplastic is linear branch, and here is not cross-linking. Here is cross-linking. You have the properties of cross-link polymers, and you have the properties of non-cross-link properties. The most important is you can, here you can recycle this, and here you don't. So what are the vitrimers? The vitrimers, they bridge these two different, completely different polymeric families. So there are both. There are both. There are thermosets and there are also thermoplastic. So because there is an exchange of the dynamic covalent bond, that time they have the flexibility to be to do the recycling. Gent is working a lot. Philippe Dupré is working a lot, but not on the macromolecular architecture. He's working on the vitrimers. Now, this is the reaction, acetaldehyde and the amino groups. And here, how we prepare by anionic polymerization, alpha omega dihydroxy polyisoprene. I don't think that until now the vitrimers in the literature, they are model. Okay? They just introduce a few groups along the chain, and after they do the network. Now, and we react with the triamine, and you can see here that the precursor are liquid, and the product is the solid. And you can prove here by NMR, by Fourier transform IR, that here is before the formation of the vitrimer, and here the aldehyde is not present, is the formation of the vitrimers. And now, by other method, by stress relaxation measurement, you can calculate the relaxation time, and you can prove that this is an Arrhenius behavior. So these are not the usual polymers, but there are these are because of the exchange. Now let's go to the non-covalent polystyrene, stereocomplex, and polyisoprene. Now these are the three guys that they work on that. Dr. Vico, Dr. Konstantinos, and Dr. George. And what we are doing is the following. As you know, the lactide has two chiral centers, here and here. So there are three isomers, two isotactic, polyalactide, polydilactide, one syndiotactic, which is the lactide that is atactic. Of course, there is the chirality, there are isomers, but it's not regular. So what does it mean that? It means that if the melting point is 160 to 180, but when we mix that, the melting point is going to 210 to 230. So it means that the D-lactide, the L-lactide, polylactide, of course, there are both 10-3 helices. It means that in three paths, they have 10 monomer units. In the case of the stereocomplex, the packing is very good, and because now the conformation is changed from 10 to 1 to 3 to 1. It means that every three here paths, the has 9 monomer units. So here also we make in the beginning the omega hydroxy terminated polyisoprene and polystyrene, and we use that as macro initiator to polymerize the L-lactide, the D-lactide. So here we make two diblock copolymers. The one is polystyrene, poly-DLA, and the other is polyisoprene. This is not polystyrene, it's polyisoprene PLLA. And we make the complexation. And you can see here that is very clear that here is the synthesis, very low polydispersity, and you can see here the PS. We make different sets of amorphous and different sets of the two isomers, PDLA and PLLA, and you can see here that they were very well defined and very low polydispersity. So here is to prove that it was only one species in the case of the two block copolymers. This is the diffusion ordered spectroscopy. How we do the stereocomplex, the diblock copolymer stereocomplex, we dissolve in dichloromethane, methane, and after you mix, and we precipitate with methanol, and we ultracentrifuge, and we have the stereocomplex, but it's the block copolymer, and we do all the measurements. I'm going to skip this NMR. How much time I have? 5 minutes? Okay. So here you can see that when you form the stereocomplex, the TM is going very high, 60 degrees higher. The L, the two block copolymers, they have 155. Here is 220. The same here, the same here, the same situation in all the pair we have studied. So this is not in order to study the block copolymers. It's to use this for making different macromolecular architecture. This is the goal. And here you can see that the wave number of the carbonyl, if you have the two polylactides, the D and the L is 7D55, but when you have the stereocomplex is going to 7D50 is the carbonyl, and this is a measure of this is a proof that there is a hydrogen bonding between the CH and the carbonyl. The CH of the lactide and the carbonyl of the lactide, of the two diblock copolymers. Here is, of course, an excellent proof is the specific rotation. Here is the PLLA, pure, and here is the PDLA, and you can see that the cotton effect is positive, the other is negative, but if you have the stereocomplex, is 0. And the other is exactly the same case in the case of the diblock. You have the diblock, and you have the positive, negative, and you have the stereocomplex is 0. Now, we did the DSC results, and you can see again that the two block copolymers with L and D, they have a lower TM than the stereocomplex. And we confirm these results by doing the diffraction pattern. This is not DSC results, okay? This is X-ray scattering. So by that, this is my last slide. Now the slide which is before my last slide. And here is non-static covalent bond based architecture. This is a new challenge for polymer chemistry and polymer physicists. And this is the group who is doing the work. Thank you very much.
Thank you, sir. It's very nice, excellent presentation for new methodologies, for the new architects. So now it is open for discussion. If you have any suggestions, sir, please.
It was really very beautiful talk. The sample preparations, I was just wondering the collaborative effort of the TM work and the small angle with Ned Thomas. How was the samples prepared? I mean, just you
No, these are Ramakrishna. This is the best results. So the thing is that, in my opinion, that if you have TM, you choose the area But if you have sacs, you cannot choose the area. This is much bigger.
No, but I was just
So,
wondering, how are you forming the hydrogen bonded complex? Do you pre-form it and then allow it, or
how
did you form that complex between
the complex? I mean, there are two kinds. There is in solution and in solid state. Okay, TM and the sacs is by solid. Yeah, solid. So the one is in solvent, and we make directly the NMR. The other we precipitate together, and we evaporate the solvent, and after we put in the vacuum oven. But there is a problem again. Okay.
Yeah.
Thank you,
But
sir.
this is like that.
Yeah, Professor Nikos, very interesting talk. So in the last part of the talk, where you have done the stereo complexation between the block copolymers, did you get any TEM image for that as an evidence of, like for example, you have two different block copolymers with different morphologies.
Okay.
When you form a stereo complex, what will be their morphology? Because I have not seen any TEM or SAC scattering cause for that.
Okay, we have done, I mean, we have only we have done only atomic force microscopy. Okay. But we see something, this is in the paper, okay. But we have to do transmission electron microscopy. We have done by ourselves. Okay. So, and we have done another thing, you know. You cannot do GPC in these samples. You know why? In solution, you cannot see the stereo complexation.
Okay, thank you very much, sir. Let us put hands together for this very interesting talk.